Learning objectives. In this chapter, the user would learn the following in detail: input-output systems, input-output hardware, application input-output interface, kernel input-output, subsystem, transforming input-output requests to hardware operations, performance, synchronous input-output and asynchronous input-output, file caching, secondary storage structure, disk scheduling, disk management, swap space management, disk reliability, stable storage implementation, tertiary storage structure, tertiary storage devices, operating system jobs, performance issues file system formats, CDFS, FAT, NTFS, exFAT, etc., kernel mode and user mode driver framework. Application input-output interface. In this section, we discuss structuring techniques and interfaces for the operating system that enables input-output devices to be treated in a standard, uniform way. We explain, for instance, how an application can open a file on a disk without knowing what kind of disk it is and how new disks and other devices can be added to a computer without disruption of the operating system. Like other complex software engineering problems, the approach here involves abstraction, encapsulation, and software layering. Specifically, we can abstract away the detailed differences in input-output devices by identifying a few general kinds. Each general kind is accessed through a standardized set of functions and interface. The differences are encapsulated in kernel modules called device drivers that internally are custom-tailored to specific devices but that export one of the standard interfaces. Figure below illustrates how the input-output related portions of the kernel are structured in software layers. The purpose of the device driver layer is to hide the differences among device controllers from the input-output subsystem of the kernel, much as the input-output system calls encapsulate the behavior of devices in a few generic classes that hide hardware differences from applications. Making the input-output subsystem independent of the hardware simplifies the job of the operating system developer. It also benefits the hardware manufacturers. They either design new devices to be compatible with an existing host controller interface such as SATA, or they write device drivers to interface the new hardware to popular operating systems. Thus, we can attach new peripherals to a computer without waiting for the operating system vendor to develop support code. Unfortunately, for device hardware manufacturers, each type of operating system has its own standards for the device driver interface. A given device may ship with multiple device drivers, for instance, drivers for Windows, Linux, AIX, and Mac OS X. Devices vary on many dimensions as illustrated in figure below, a kernel input-output structure. Character stream or block. A character stream device transfers bytes one by one, whereas a block device transfers a block of bytes as a unit. Sequential or random access. A sequential device transfers data in a fixed order determined by the device, whereas the user of a random access device can instruct the device to seek to any of the available data storage locations. Synchronous or asynchronous. A synchronous device performs data transfers with predictable response times in coordination with other aspects of the system. An asynchronous device exhibits irregular or unpredictable response times not coordinated with other computer events. Shareable or dedicated. A shareable device can be used concurrently by several processes or threads. A dedicated device cannot. Speed of operation. Device speeds range from a few bytes per second to a few gigabytes per second. Read, write, read-only or write-only. Some devices perform both input and output, but others support only one data transfer direction. For the purpose of application access, many of these differences are hidden by the operating system and the devices are grouped into a few conventional types. The resulting styles of device access have been found to be useful and broadly applicable. Although the exact system calls may differ across operating systems, the device categories are fairly standard. The major access conventions include block input-output, character stream input-output, memory map file access, and network sockets. Operating systems also provide special system calls to access a few additional devices, such as a time-of-day clock and a timer. Some operating systems provide a set of system calls for graphical display, video, and audio devices. Most operating systems also have an escape or backdoor that transparently passes arbitrary commands from an application to a device driver. In Unix, the system call is IOCTL function for input-output control. The IOCTL function system call enables an application to access any functionality that can be implemented by any device driver without the need to invent a new system call. The IOCTL function system call has 3 arguments. The first is a file descriptor that connects the application to the driver by referring to a hardware device managed by that driver. The second is an integer that selects one of the commands implemented in the driver. The third is a pointer to an arbitrary data structure in memory that enables the application and driver to communicate any necessary control information or data. Block and character devices. The block device interface captures all the aspects necessary for accessing disk drives and other block-oriented devices. The device is expected to understand commands such as read function and write function. If it is a random access device, it is also expected to have a seek function command to specify which block to transfer next. Applications normally access such a device through a file system interface. We can see that read function, write function, and seek function capture the essential behaviors of a block storage devices so that applications are insulated from the low-level differences among those devices. The operating system itself, as well as special applications such as database management systems, may prefer to access a block device as a simple linear array of blocks. This mode of access is sometimes called raw input-output. If the application performs its own buffering, then using a file system would cause extra unneeded buffering. Likewise, if an application provides its own locking of file blocks or regions, then any operating system locking services would be redundant at the least and contradictory at the worst. To avoid these conflicts, raw device access passes control of the device directly to the application, letting the operating system step out of the way. Unfortunately, no operating system services are then performed on this device. A compromise that is becoming common is for the operating system to allow a mode of operation on a file that disables buffering and locking. In the Unix world, this is called direct input-output. Memory mapped file access can be layered on top of block device drivers. Rather than offering read and write operations, a memory map interface provides access to disk storage via an array of bytes in main memory. The system call that maps a file into memory returns the virtual memory address that contains a copy of the file. The actual data transfers are performed only when needed to satisfy access to the memory image. Because the transfers are handled by the same mechanism as that used for demand-paged virtual memory access, memory mapped input-output is efficient. Memory mapping is also convenient for programmers. Access to a memory mapped file is as simple as reading from and writing to memory. Operating systems that offer virtual memory commonly use the mapping interface for kernel services. For instance, to execute a program, the operating system maps the executable into memory and then transfers control to the entry address of the executable. The mapping interface is also commonly used for kernel access to swap space on disk. A keyboard is an example of a device that is accessed through a character stream interface. The basic system calls in this interface enable an application to get function or put function one character. On top of this interface, libraries can be built that offer line-at-a-time access with buffering and editing services. For example, when a user types a backspace, the preceding character is removed from the input stream. This style of access is convenient for input devices such as keyboards, mice, and modems that produce data for input spontaneously, that is, at times that cannot necessarily be predicted by the application. This access style is also good for output devices such as printers and audio boards, which naturally fit the concept of a linear stream of bytes. Network devices. Because of the performance and addressing characteristics of network input-output differ significantly from those of disk input-output, most operating systems provide a network input-output interface that is different from the read function, write function, seek function interface used for disks. One interface available in many operating systems, including Unix and Windows, is the network socket interface. Think of a wall socket for electricity. Any electrical appliance can be plugged in. By analogy, the system calls in the socket interface enable an application to create a socket to connect a local socket to a remote address, which plugs this application into a socket created by another application, to listen for any remote application to plug into the local socket, and to send and receive packets over the connection. To support the implementation of servers, the socket interface also provides a function called select function that manages a set of sockets. A call to select function returns information about which sockets have a packet waiting to be received and which sockets have room to accept a packet to be sent. The use of select function eliminates the polling and busy waiting that would otherwise be necessary for the network input-output. These functions encapsulate the essential behaviors of networks, greatly facilitating the creation of distributed applications that can use any underlying network hardware and protocol stack. Many other approaches to inter-process communication and network communication have been implemented. For instance, Windows provides one interface to the network interface card and a second interface to the network protocols. In Unix, which has a long history as a proving ground for network technology, we find half-duplex pipes, full-duplex FIFOs, full-duplex streams, message queues, and sockets. Clocks and timers. Most computers have hardware clocks and timers that provide three basic functions: give the current time, give the elapsed time, set a timer to trigger operation X at a time. These functions are used heavily by the operating system as well as by time-sensitive applications. Unfortunately, the system calls that implement these functions are not standardized across operating systems. The hardware to measure elapsed time and to trigger operations is called a programmable interval timer. It can be set to wait a certain amount of time and then generate an interrupt, and it can be set to do this once or to repeat the process to generate periodic interrupts. The scheduler uses this mechanism to generate an interrupt that will preempt a process at the end of its time slice. The disk input-output subsystem uses it to invoke the periodic flushing of dirty cache buffers to disk, and the network subsystem uses it to cancel operations that are proceeding too slowly because of network congestion or failures. The operating system may also provide an interface for user processes to use timers. The operating system can support more timer requests than the number of timer hardware channels by simulating virtual clocks. To do so, the kernel or the timer device driver maintains a list of interrupts wanted by its own routines and by user requests, sorted in earliest time first order. It sets the timer for the earliest time. When the timer interrupts, the kernel signals the requester and reloads the timer with the next earliest time. On many computers, the interrupt rate generated by the hardware clock is between 18 and 60 ticks per second. This resolution is coarse since a modern computer can execute hundreds of millions of instructions per second. The precision of triggers is limited by the coarse resolution of the timer together with the overhead of maintaining virtual clocks. Furthermore, if the timer ticks are used to maintain the system time of day clock, the system clock can drift. In most computers, the hardware clock is constructed from a high-frequency counter. In some computers, the value of this counter can be read from a device register, in which case the counter can be considered a high-resolution clock. Although this clock does not generate interrupts, it offers accurate measurements of time intervals. Non-blocking and asynchronous input-output. Another aspect of the system call interface relates to the choice between blocking input-output and non-blocking input-output. When an application issues a blocking system call, the execution of the application is suspended. The application is moved from the operating system's run queue to a wait queue. After the system call completes, the application is moved back to the run queue where it is eligible to resume execution. When it resumes execution, it will receive the values returned by the system call. The physical actions performed by input-output devices are generally asynchronous. They take a varying or unpredictable amount of time. Nevertheless, most operating systems use blocking system calls for the application interface because blocking application code is easier to understand than non-blocking application code. Some user-level processes need non-blocking input-output. One example is a user interface that receives keyboard and mouse input while processing and displaying data on the screen. Another example is a video application that reads frames from a file on disk while simultaneously decompressing and displaying the output on the display. One way an application writer can overlap execution with input-output is to write a multi-threaded application. Some threads can perform blocking system calls while others continue executing. Some operating systems provide non-blocking input-output system calls. A non-blocking call does not halt the execution of the application for an extended time. Instead, it returns quickly with a return value that indicates how many bytes were transferred. An alternative to a non-blocking system call is an asynchronous system call. An asynchronous call returns immediately without waiting for the input-output to complete. The application continues to execute its code. The completion of the input-output at some future time is communicated to the application either through the setting of some variable in the address space of the application or through the triggering of a signal or software interrupt or a call block routine that is executed outside the linear control flow of the application. The difference between non-blocking and asynchronous system calls is that a non-blocking read function returns immediately with whatever data are available, the full number of bytes requested, fewer, or none at all. An asynchronous read function call requests a transfer that will be performed in its entirety but will complete at some future time. These two input-output methods are shown in figure below. Two input-output methods, A. Synchronous, B. Asynchronous. Asynchronous activities occur throughout modern operating systems. Frequently, they are not exposed to users or applications but rather are contained within the operating system operation. Disk and network input-output are useful examples. By default, when an application issues a network send request or a disk write request, the operating system notes the request, buffers the input-output and returns to the application. When possible, to optimize overall system performance, the operating system completes the request. If a system failure occurs in the interim, the application will lose any in-flight requests. Therefore, operating systems usually put a limit on how long they will buffer a request. Some versions of Unix flush their disk buffers every 30 seconds, for example, or each request is flushed within 30 seconds of its occurrence. Data consistency within applications is maintained by the kernel, which reads data from its buffers before issuing input-output requests to devices, assuring that data not yet written are nevertheless returned to a requesting reader. Note that multiple threads performing input-output to the same file might not receive consistent data depending on how the kernel implements its input-output. In this situation, the threads may need to use locking protocols. Some input-output requests need to be performed immediately, so input-output system calls usually have a way to indicate that a given request or input-output to a specific device should be performed synchronously. A good example of non-blocking behavior is the select function system call for network sockets. This system call takes an argument that specifies a maximum waiting time. By setting it to 0, an application can poll for network activity without blocking. But using select function introduces extra overhead because the select function call only checks whether input-output is possible. For a data transfer, select function must be followed by some kind of read function or write function command. A variation on this approach, found in Mac, is a blocking multiple read call. It specifies desired reads for several devices in one system call and returns as soon as any one of them completes. Vectored input-output. Some operating systems provide another major variation of input-output via their application's interfaces. Vectored input-output allows one system call to perform multiple input-output operations involving multiple locations. For example, the Unix ready system call accepts a vector of multiple buffers and either reads from a source to that vector or writes from that vector to a destination. The same transfer could be caused by several individual invocations of system calls, but this scatter-gather method is useful for a variety of reasons. Multiple separate buffers can have their contents transferred via one system call, avoiding context switching and system call overhead. Without vectored input-output, the data might first need to be transferred to a larger buffer in the right order and then transmitted, which is inefficient. In addition, some versions of scatter-gather provide atomicity, assuring that all the input-output is done without interruption, and avoiding corruption of data if other threads are also performing input-output involving those buffers. When possible, programmers make use of scatter-gather input-output features to increase throughput and decrease system overhead. Disk management. The operating system is responsible for several other aspects of disk management too. Here we discuss disk initialization, booting from disk, and bad block recovery. Disk formatting. A new magnetic disk is a blank slate. It is just a platter of a magnetic recording material. Before a disk can store data, it must be divided into sectors that the disk controller can read and write. This process is called low-level formatting or physical formatting. Low-level formatting files the disk with a special data structure for each sector. The data structure for a sector typically consists of a header, a data area usually 512 bytes in size, and a trailer. The header and trailer contain information used by the disk controller, such as a sector number and an error correcting code, ECC. When the controller writes a sector of data during normal input-output, the ECC is updated with a value calculated from all the bytes in the data area. When the sector is read, the ECC is recalculated and compared with the stored value. If the stored and calculated numbers are different, this mismatch indicates that the data area of the sector has become corrupted and that the disk sector may be bad. The ECC is an error-correcting code because it contains enough information, if only a few bits of data have been corrupted, to enable the controller to identify which bits have changed and calculate what their correct values should be. It then reports a recoverable soft error. The controller automatically does the ECC processing whenever a sector is read or written. Most hard disks are low-level formatted at the factory as a part of the manufacturing process. This formatting enables the manufacturer to test the disk and to initialize the mapping from logical block numbers to defect-free sectors on the disk. For many hard disks, when the disk controller is instructed to low-level format the disk, it can also be told how many bytes of data space to leave between the header and trailer of all sectors. It is usually possible to choose among a few sizes such as 256, 512 and 1024 bytes. Formatting a disk with a larger sector size means that fewer sectors can fit on each track, but it also means that fewer headers and trailers are written on each track and more space is available for user data. Some operating systems can handle only a sector size of 512 bytes. Before it can use a disk to hold files, the operating system still needs to record its own data structures on the disk. It does so in two steps. The first step is to partition the disk into one or more groups of cylinders. The operating system can treat each partition as though it were a separate disk. For instance, one partition can hold a copy of the operating system's executable codes while another holds user files. The second step is logical formatting or creation of a file system. In this step, the operating system stores the initial file system data structures onto the disk. These data structures may include maps of free and allocated space and an initial empty directory. To increase efficiency, most file systems group blocks together into larger chunks, frequently called clusters. Disk input-output is done via blocks, but file system input-output is done via clusters, effectively assuring that input-output has more sequential access and fewer random access characteristics. Some operating systems give special programs the ability to use a disk partition as a large sequential array of logical blocks without any file system data structures. This array is sometimes called the raw disk, and input-output to this array is termed raw input-output. For example, some database systems prefer raw input-output because it enables them to control the exact disk location where each database record is stored. Raw input-output bypasses all the file system services such as the buffer cache, file locking, prefetching, space allocation, file names, and directories. We can make certain applications more efficient by allowing them to implement their own special-purpose storage services on a raw partition, but most applications perform better when they use the regular file system services. Boot block. For a computer to start running, for instance, when it is powered up or rebooted, it must have an initial program, bootstrap program, to run. It initializes all aspects of the system from CPU registers to device controllers and the contents of main memory and then starts the operating system. To do its job, Bootstrap program finds the operating system kernel on disk, loads that kernel into memory and jumps to an initial address to begin the operating system execution. For most computers, the Bootstrap is stored in read-only memory, ROM. Since ROM is read-only, it cannot be infected by a computer virus. This location is convenient because ROM needs no initialization and is at a fixed location that the processor can start executing when powered up or reset. The problem is that changing this Bootstrap code requires changing the ROM hardware chips. For this reason, most systems store a tiny Bootstrap loader program in the boot ROM whose only job is to bring in a full Bootstrap program from disk. The full Bootstrap program can be changed easily. A new version is simply written onto the disk. The full Bootstrap program is stored in the boot blocks at a fixed location on the disk. A disk that has a boot partition is called a boot disk or system disk. The code in the boot ROM instructs the disk controller to read the boot blocks into memory. No device drivers are loaded at this point, and then starts executing that code. The full Bootstrap program is more sophisticated than the Bootstrap loader in the boot ROM. It is able to load the entire operating system from a non-fixed location on disk and to start the operating system running. Even so, the full Bootstrap code may be small. Let's consider as an example the boot process in Windows. First, note that Windows allows a hard disk to be divided into partitions, and one partition, identified as the boot partition, contains the operating system and device drivers. The Windows system places its boot code in the first sector on the hard disk, which it terms the Master Boot Record, or MBR. Booting begins by running code that is resident in the system's ROM memory. This code directs the system to read the boot code from the MBR. In addition to containing boot code, the MBR contains a table listing the partitions for the hard disk and a flag indicating which partition the system is to be booted from, as illustrated in figure below. Once the system identifies the boot partition, it reads the first sector from that partition, which is called the boot sector, and continues with the remainder of the boot process, which includes loading the various subsystems and system services. Bad blocks. Because disks have moving parts and small tolerances, recall that the disk head flies just above the disk surface. They are prone to failure. Sometimes the failure is complete. In this case, the disk needs to be replaced and its contents restored from backup media to the new disk. More frequently, one or more sectors become defective. Most disks even come from the factory with bad blocks. Depending on the disk and controller in use, these blocks are handled in a variety of ways. On simple disks, such as some disks with IDE controllers, bad blocks are handled manually. One strategy is to scan the disk to find bad blocks while the disk is being formatted. Any bad blocks that are discovered are flagged as unusable so that the file system does not allocate them. If blocks go bad during normal operation, a special program such as the Linux bad blocks command must be run manually to search for the bad blocks and to lock them away. Data that resided on the bad blocks usually are lost. More sophisticated disks are smarter about bad block recovery. The controller maintains a list of bad blocks on the disk. The list is initialized during the low-level formatting at the factory and is updated over the life of the disk. Low-level formatting also sets aside spare sectors not visible to the operating system. The controller can be told to replace each bad sector logically with one of the spare sectors. This scheme is known as sector sparing or forwarding. A typical bad sector transaction might be as follows. The operating system tries to read logical block 87. The controller calculates the ECC and finds that the sector is bad. It reports this finding to the operating system. The next time the system is rebooted, a special command is run to tell the controller to replace the bad sector with a spare. After that, whenever the system requests logical block 87, the request is translated into the replacement sector's address by the controller. Note that such a redirection by the controller could invalidate any optimization by the operating system's disk scheduling algorithm. For this reason, most disks are formatted to provide a few spare sectors in each cylinder and a spare cylinder as well. When a bad block is remapped, the controller uses a spare sector from the same cylinder if possible. As an alternative to sector sparing, some controllers can be instructed to replace a bad block by sector slipping. Here is an example. Suppose that logical block 17 becomes defective and the first available spare follows sector 202. Sector slipping then remaps all the sectors from 17 to 202, moving them all down one spot. That is, sector 202 is copied into the spare, then sector 201 into 202, then 200 into 201, and so on until sector 18 is copied into sector 19. Slipping the sectors in this way frees up the space of sector 18 so that sector 17 can be mapped to it. The replacement of a bad block generally is not totally automatic because the data in the bad block are usually lost. Soft errors may trigger a process in which a copy of the block data is made and the block is spared or slipped. An unrecoverable hard error, however, results in lost data. Whatever file was using that block must be repaired, for instance, by restoration from a backup tape, and that requires manual intervention. Disk reliability. Several improvements in disk use techniques involve the use of multiple disks working cooperatively. Disk stripping uses a group of disks as one, improves performance by breaking blocks into sub-blocks. RAID, redundant array of independent disks, schemes improve performance and improve the reliability of the storage system by storing redundant data. Mirroring or shadowing keeps duplicate of each disk. Block interleaved parity uses much less redundancy. RAID structure. Disk drives have continued to get smaller and cheaper, so it is now economically feasible to attach many disks to a computer system. Having a large number of disks in a system presents opportunities for improving the rate at which data can be read or written if the disks are operated in parallel. Furthermore, this setup offers the potential for improving the reliability of data storage because redundant information can be stored on multiple disks. Thus, failure of one disk does not lead to loss of data. A variety of disk organization techniques, collectively called redundant arrays of independent disks, RAID, are commonly used to address the performance and reliability issues. In the past, RAIDs composed of small, cheap disks were viewed as a cost-effective alternative to large, expensive disks. Today, RAIDs are used for their higher reliability and higher data transfer rate rather than for economic reasons. Hence, the I in RAID, which once stood for inexpensive, now stands for independent. Improvement of reliability via redundancy. Let's first consider the reliability of RAIDs. The chance that some disk out of a set of n disks will fail is much higher than the chance that a specific single disk will fail. Suppose that the mean time to failure of a single disk is 100,000 hours, then the mean time to failure of some disk in an array of 100 disks will be 100,000 divided by 100 equals 1,000 hours or 41.66 days, which is not long at all. If we store only one copy of the data, then each disk failure will result in loss of a significant amount of data, and such a high rate of data loss is unacceptable. The solution to the problem of reliability is to introduce redundancy. We store extra information that is not normally needed, but that can be used in the event of failure of a disk to rebuild the lost information. Thus, even if a disk fails, data are not lost. The simplest but most expensive approach to introducing redundancy is to duplicate every disk. This technique is called mirroring. With mirroring, a logical disk consists of two physical disks, and every write is carried out on both disks. The result is called a mirrored volume. If one of the disks in the volume fails, the data can be read from the other. Data will be lost only if the second disk fails before the first failed disk is replaced. The mean time to failure of a mirrored volume, where failure is the loss of data, depends on two factors. One is the mean time to failure of the individual disks. The other is the mean time to repair, which is the time it takes on average to replace a failed disk and to restore the data on it. Suppose that the failures of the two disks are independent, that is, the failure of one disk is not connected to the failure of the other. Then, if the mean time to failure of a single disk is 100 hours and the mean time to repair is 10 hours, the mean time to data loss of a mirrored disk system is 1,000,002 divided by brackets 2 times 10 equals 500 times 10 to the power of 6 hours or 57,000 years. We should be aware that we cannot really assume that disk failures will be independent. Power failures and natural disasters such as earthquakes, fires, and floods may result in damage to both disks at the same time. Also, manufacturing defects in a batch of disks can cause correlated failures. As disks age, the probability of failure grows, increasing the chance that a second disk will fail while the first is being repaired. In spite of all these considerations, however, mirrored disk systems offer much higher reliability than do single disk systems. Power failures are a particular source of concern since they occur far more frequently than do natural disasters. Even with mirroring of disks, if writes are in progress to the same block in both disks and power fails before both blocks are fully returned, the two blocks can be in an inconsistent state. One solution to this problem is to write one copy first, then the next. Another is to add a solid-state non-volatile RAM (NVRAM) cache to the RAID array. This write-back cache is protected from data loss during power failures, so the write can be considered complete at that point, assuming the NVRAM has some kind of error protection and correction, such as ECC or mirroring. Improvement in performance via parallelism. Now let's consider how parallel access to multiple disks improves performance. With disk mirroring, the rate at which read requests can be handled is doubled, since read requests can be sent to either disk as long as both disks in a pair are functional, as is almost always the case. The transfer rate of each read is the same as in a single disk system, but the number of reads per unit time has doubled. With multiple disks, we can improve the transfer rate as well, or instead, by stripping data across the disks. In its simplest form, data stripping consists of splitting the bits of each byte across multiple disks. Such stripping is called bit-level stripping. For example, if we have an array of 8 disks, we write bit I of each byte to disk I. The array of 8 disks can be treated as a single disk with sectors that are 8 times the normal size and, more important, that have 8 times the access rate. Every disk participates in every access, read or write, so the number of accesses that can be processed per second is about the same as on a single disk, but each access can read 8 times as many data in the same time as on a single disk. Bit-level stripping can be generalized to include a number of disks that either is a multiple of 8 or divides 8. For example, if we use an array of 4 disks, bits I and 4 plus I of each byte go to disk I. Further, stripping need not occur at the bit level. In block-level stripping, for instance, blocks of a file are stripped across multiple disks. With n disks, block I of a file goes to disk I mod n plus 1. Other levels of stripping, such as bytes of a sector or sectors of a block, also are possible. Block-level stripping is the most common. Parallelism in a disk system as achieved through stripping has two main goals. Increase the throughput of multiple small accesses, that is, page accesses by load balancing. Reduce the response time of large accesses. RAID levels. Mirroring provides high reliability, but it is expensive. Stripping provides high data transfer rates, but it does not improve reliability. Numerous schemes to provide redundancy at lower cost by using disk stripping combined with parity bits, which we will describe shortly, have been proposed. These schemes have different cost-performance trade-offs and are classified according to levels called RAID levels. We describe the various levels here. Figure shows them pictorially. In the figure, P indicates error correcting bits and C indicates a second copy of the data. In all cases depicted in the figure, 4 disks worth of data are stored and the extra disks are used to store redundant information for failure recovery. RAID Level 0. RAID Level 0 refers to disk arrays with stripping at the level of blocks but without any redundancy, such as mirroring or parity bits as shown in figure above A. RAID Level 1. RAID Level 1 refers to disk mirroring. Figure above B shows a mirrored organization. RAID Level 2. RAID Level 2 is also known as Memory Style Error Correcting Code (ECC) organization. Memory systems have long detected certain errors by using parity bits. Each byte in a memory system may have a parity bit associated with it that records whether the number of bits in the byte set to 1 is even, parity equals 0, or odd, parity equals 1. If one of the bits in the byte is damaged, either as 1 becomes a 0 or a 0 becomes a 1, the parity of the byte changes and thus does not match the stored parity. Similarly, if the stored parity bit is damaged, it does not match the computed parity. Thus, all single-bit errors are detected by the memory system. Error-correcting schemes store 2 or more extra bits and can reconstruct the data if a single bit is damaged. The idea of ECC can be used directly in disk arrays via stripping of bytes across disks. For example, the first bit of each byte can be stored in disk 1, the second bit in disk 2, and so on until the 8th bit is stored in disk 8. The error correction bits are stored in further disks. This scheme is shown in figure above C, where the disks labeled P store the error correction bits. If one of the disks fails, the remaining bits of the byte and the associated error correction bits can be read from other disks and used to reconstruct the damaged data. Note that RAID Level 2 requires only 3 disks overhead for 4 disks of data, unlike RAID Level 1, which requires 4 disks overhead. RAID Level 3. RAID Level 3 or Bit Interleaved Parity Organization improves on Level 2 by taking into account the fact that, unlike memory systems, disk controllers can detect whether a sector has been read correctly, so a single parity bit can be used for error correction as well as for detection. The idea is as follows. If one of the sectors is damaged, we know exactly which sector it is and we can figure out whether any bit in the sector is a 1 or a 0 by computing the parity of the corresponding bits from sectors in the other disks. If the parity of the remaining bits is equal to the stored parity, the missing bit is 0. Otherwise, it is 1. RAID Level 3 is as good as Level 2 but is less expensive in the number of extra disks required. It has only a 1 disk overhead, so Level 2 is not used in practice. Level 3 is shown pictorially in figure above D. RAID Level 3 has 2 advantages over Level 1. First, the storage overhead is reduced because only 1 parity disk is needed for several regular disks, whereas 1 mirror disk is needed for every disk in Level 1. Second, since reads and writes of a byte are spread out over multiple disks with n-way stripping of data, the transfer rate for reading or writing a single block is n times as fast as with RAID Level 1. On the negative side, RAID Level 3 supports fewer input-outputs per second since every disk has to participate in every input-output request. A further performance problem with RAID 3 and with all parity-based RAID levels is the expense of computing and writing the parity. This overhead results in significantly slower writes than with non-parity RAID arrays. To moderate this performance penalty, Many RAID storage arrays include a hardware controller with dedicated parity hardware. This controller offloads the parity computation from the CPU to the array. The array has an NVRAM cache as well to store the blocks while the parity is computed and to buffer the writes from the controller to the spindles. This combination can make parity RAID almost as fast as non-parity. In fact, a caching array doing parity RAID can outperform a non-caching non-parity RAID. RAID Level 4. RAID Level 4, or Block Interleaved Parity Organization, uses block level stripping as in RAID 0 and in addition keeps a parity block on a separate disk for corresponding blocks from n other disks. The scheme is diagrammed in figure above E. If one of the disks fails, the parity block can be used with the corresponding blocks from the other disks to restore the blocks of the failed disk. A block read accesses only one disk, allowing other requests to be processed by the other disks. Thus, the data transfer rate for each access is slower, but multiple read accesses can proceed in parallel, leading to a higher overall input-output rate. The transfer rates for large reads are high since all the disks can be read in parallel. Large writes also have higher transfer rates since the data and parity can be written in parallel. Small independent writes cannot be performed in parallel. An operating system write of data smaller than a block requires that the block be read, modified with the new data, and written back. The parity block has to be updated as well. This is known as the read-modify-write cycle. Thus, a single write requires 4 disk accesses, 2 to read the 2 old blocks and 2 to write the 2 new blocks. WAFL uses RAID level 4 because this RAID level allows disks to be added to a RAID set seamlessly. If the added disks are initialized with blocks containing only zeros, then the parity value does not change and the RAID set is still correct. RAID Level 5. RAID Level 5, or Block Interleaved Distributed Parity, differs from Level 4 in that it spreads data and parity among all n+1 disks rather than storing data in n disks and parity in one disk. For each block, one of the disks stores the parity and the others store data. For example, with an array of 5 disks, the parity for the nth block is stored in disk n mod 5 plus 1. The nth blocks of the other 4 disks store actual data for that block. This setup is shown in figure above, F, where the P's are distributed across all the disks. A parity block cannot store parity for blocks in the same disk because a disk failure would result in loss of data as well as of parity, and hence the loss would not be recoverable. By spreading the parity across all the disks in the set, RAID 5 avoids potential overuse of a single parity disk which can occur with RAID 4. RAID 5 is the most common parity RAID system. RAID Level 6. RAID Level 6, also called the P plus Q redundancy scheme, is much like RAID Level 5 but stores extra redundant information to guard against multiple disk failures. Instead of parity, error-correcting codes such as the Reed-Solomon codes are used. In the scheme shown in figure above, G, 2 bits of redundant data are stored for every 4 bits of data compared with 1 parity bit in level 5, and the system can tolerate 2 disk failures. RAID levels 0 plus 1 and 1 plus 0. RAID level 0 plus 1 refers to a combination of RAID levels 0 and 1. RAID 0 provides the performance while RAID 1 provides the reliability. Generally, this level provides better performance than RAID 5. It is common in environments where both performance and reliability are important. Unfortunately, like RAID 1, it doubles the number of disks needed for storage, so it is also relatively expensive. In RAID 0+1, a set of disks are stripped, and then the stripe is mirrored to another equivalent stripe. Another RAID option that is becoming available commercially is RAID level 1+0, in which disks are mirrored in pairs and then the resulting mirror paired are stripped. This scheme has some theoretical advantages over RAID 0+1. For example, if a single disk fails in RAID 0+1, an entire stripe is inaccessible, leaving only the other stripe. With a failure in RAID 1+0, a single disk is unavailable, but the disk that mirrors it is still available, as are all the rest of the disks. Figure below. Numerous variations have been proposed to the basic RAID schemes described here. As a result, some confusion may exist about the exact definitions of the different RAID levels. The implementation of RAID is another area of variation. Consider the following layers at which RAID can be implemented. Volume management software can implement RAID within the kernel or at the system software layer. In this case, the storage hardware can provide minimal features and still be part of a full RAID solution. Parity RAID is fairly slow when implemented in software, so typically RAID 0, 1, or 0+1 is used. RAID can be implemented in the host bus adapter HBA hardware. Only the disks directly connected to the HBA can be part of a given RAID set. This solution is low in cost but not very flexible. RAID can be implemented in the hardware of the storage array. The storage array can create RAID sets of various levels and can even slice these sets into smaller volumes, which are then presented to the operating system. The operating system need only implement the file system on each of the volumes. Arrays can have multiple connections available or can be part of a SAN, allowing multiple hosts to take advantage of the array's features. RAID can be implemented in the SAN interconnect layer by disk virtualization devices. In this case, a device sits between the hosts and the storage. It accepts commands from the servers and manages access to the storage. It could provide mirroring, for example, by writing each block to two separate storage devices. Other features, such as snapshots and replication, can be implemented at each of these levels as well. A snapshot is a view of the file system before the last update took place. Replication involves the automatic duplication of writes between separate sites for redundancy and disaster recovery. Replication can be synchronous or asynchronous. In synchronous replication, each block must be written locally and remotely before the write is considered complete, whereas in asynchronous replication, the writes are grouped together and written periodically. Asynchronous replication can result in data loss if the primary site fails, but it is faster and has no distance limitations. The implementation of these features differs depending on the layer at which RAID is implemented. For example, if RAID is implemented in software, then each host may need to carry out and manage its own replication. If replication is implemented in the storage array or in the SAN interconnect, however, then whatever the host operating system or its features, the host's data can be replicated. One other aspect of most RAID implementations is a hot spare disk or disks. A hot spare is not used for data but is configured to be used as a replacement in case of disk failure. For instance, a hot spare can be used to rebuild a mirrored pair should one of the disks in the pair fail. In this way, the RAID level can be re-established automatically without waiting for the failed disk to be replaced. Allocating more than one hot spare allows more than one failure to be repaired without human intervention. Selecting a RAID level. Given the many choices they have, how do system designers choose a RAID level? One consideration is rebuild performance. If a disk fails, the time needed to rebuild its data can be significant. This may be an important factor if a continuous supply of data is required, as it is in high-performance or interactive database systems. Furthermore, rebuild performance influences the mean time to failure. Rebuild performance varies with the RAID level used. Rebuilding is easiest for RAID level 1 since data can be copied from another disk. For the other levels, we need to access all the other disks in the array to rebuild data in a failed disk. Rebuild times can be hours for RAID 5 rebuilds of large disk sets. RAID level 0 is used in high-performance applications where data loss is not critical. RAID level 1 is popular for applications that require high reliability with fast recovery. RAID 0 plus 1 and 1 plus 0 are used where both performance and reliability are important, for example, for small databases. Due to RAID 1's high space overhead, RAID 5 is often preferred for storing large volumes of data. Level 6 is not supported currently by many RAID implementations, but it should offer better reliability than Level 5. RAID system designers and administrators of storage have to make several other decisions as well. For example, how many disks should be in a given RAID set, how many bits should be protected by each parity bit. If more disks are in an array, data transfer rates are higher, but the system is more expensive. If more bits are protected by a parity bit, the space overhead due to parity bits is lower, but the chance that a second disk will fail before the first failed disk is repaired is greater, and that will result in data loss. Disk scheduling. One of the responsibilities of the operating system is to use the hardware efficiently. For the disk drives, meeting this responsibility entails having fast access time and a large disk bandwidth. For magnetic disks, the access time has two major components. The seek time is the M time for the disk to move the heads to the cylinder containing the desired sector. The rotational latency is the additional time for the disk to rotate the desired sector to the disk head. The disk bandwidth is the total number of bytes transferred divided by the total time between the first request for service and the completion of the last transfer. We can improve both the access time and the bandwidth by managing the order in which disk input-output requests are serviced. Whenever a process needs input-output to or from the disk, it issues a system call to the operating system. The request specifies several pieces of information: whether this operation is input or output, what the disk address for the transfer is, what the memory address for the transfer is, what the number of sectors to be transferred is. If the desired disk drive and controller are available, the request can be serviced immediately. If the drive or controller is busy, any new requests for the service will be placed in the queue of pending requests for that drive. For a multi-programming system with many processes, the disk queue may often have several pending requests. Thus, when one request is completed, the operating system chooses which pending request to service next. How does the operating system make this choice? Any one of the several disk scheduling algorithms can be used, and we discuss them next. FCFS scheduling. The simplest form of disk scheduling is, of course, the first come, first served FCFS algorithm. This algorithm is intrinsically fair, but it generally does not provide the fastest service. Consider, for example, a disk queue with requests for input-output to blocks on cylinders 98, 183, 37, 122, 14, 124, 65, 67, in that order. If the disk head is initially at cylinder 53, it will first move from 53 to 98, then to 183, 37, 122, 14, 124, 65, and finally to 67 for a total head movement of 640 cylinders. This schedule is diagrammed in figure above. The wild swing from 122 to 14 and then back to 124 illustrates the problem with this schedule. If the requests for cylinders 37 and 14 could be serviced together before or after the requests for 122 and 124, the total head movement could be decreased substantially and performance could be thereby improved. SSTF scheduling. It seems reasonable to service all the requests close to the current head position before moving the head far away to service other requests. This assumption is the basis for the shortest seek time first SSTF algorithm. The SSTF algorithm selects the request with the least seek time from the current head position. In other words, SSTF chooses the pending request closest to the current head position. For our example request queue, the closest request to the initial head position 53 is at cylinder 65. Once we are at cylinder 65, the next closest request is at cylinder 67. From there, the request at cylinder 37 is closer than the one at 98, so 37 is served next. Continuing, we service the request at cylinder 14, then 98, 122, 124 and finally 183, figure below. This scheduling method results in a total head movement of only 236 cylinders, little more than 1/3 of the distance needed for FCFS scheduling of this request queue. Clearly, this algorithm gives a substantial improvement in performance. SSTF scheduling is essentially a form of shortest job first SJF scheduling, and like SJF scheduling, it may cause starvation of some requests. Remember that requests may arrive at any time. Suppose that we have two requests in the queue for cylinders 14 and 186, and while the request from 14 is being serviced, a new request near 14 arrives. This new request will be serviced next, making the request at 186 wait. While this request is being serviced, another request close to 14 could arrive. In theory, a continual stream of requests near one another could cause the request for cylinder 186 to wait indefinitely. This scenario becomes increasingly likely as the pending request queue grows longer. Although the SSTF algorithm is a substantial improvement over the FCFS algorithm, it is not optimal. In the example, we can do better by moving the head from 53 to 37, even though the latter is not closest, and then to 14, before turning around to service 65, 67, 98, 122, 124, and 183. This strategy reduces the total head movements to 208 cylinders. Scan scheduling. In the scan algorithm, the disk arm starts at one end of the disk and moves toward the other end, servicing requests as it reaches each cylinder until it gets to the other end of the disk. At the other end, the direction of head movement is reversed and servicing continues. The head continuously scans back and forth across the disk. The scan algorithm is sometimes called the elevator algorithm, since the disk arm behaves just like an elevator in a building, for servicing all the requests going up and then reversing to service requests the other way. Let's return to our example to illustrate. Before applying scan to schedule the requests on cylinders 98, 183, 37, 122, 14, 124, 65 and 67, we need to know the direction of head movement in addition to the head's current position. Assuming that the disk arm is moving towards 0 and that the initial head position is again 53, the head will next service 37 and then 14. At cylinder 0, the arm will reverse and will move toward the other end of the disk, servicing the requests at 65, 67, 98, 122, 124, and 183. Figure below. If a request arrives in the queue just in front of the head, it will be serviced almost immediately. A request arriving just behind the head will have to wait until the arm moves to the end of the disk, reverses direction, and comes back. Assuming a uniform distribution of requests for cylinders, consider the density of requests when the head reaches one end and reverses direction. At this point, relatively few requests are immediately in front of the head since these cylinders have recently been serviced. The heaviest density of requests is at the other end of the disk. These requests have also waited the longest, so why not go there first? That is the idea of the next algorithm. C-scan scheduling. Circular scan, C-scan scheduling is a variant of scan designed to provide a more uniform wait time. Like scan, C-scan moves the head from one end of the disk to the other, servicing requests along the way. When the head reaches the other end, however, it immediately returns to the beginning of the disk without servicing any requests on the return trip. Figure below. The C-scan scheduling algorithm essentially treats the cylinders as a circular list that wraps around from the final cylinder to the first one. Look scheduling. As we described them, both scan and C-scan move the disk arm across the full width of the disk. In practice, neither algorithm is often implemented this way. More commonly, the arm goes only as far as the final request in each direction. Then, it reverses direction immediately without going all the way to the end of the disk. Versions of scan and C-scan that follow this pattern are called look and C-look scheduling because they look for a request before continuing to move in a given direction. Figure below. Selection of a disk scheduling algorithm. Given so many disk scheduling algorithms, how do we choose the best one? SSTF is common and has a natural appeal because it increases performance over FCFS. Scan and C-scan perform better for systems that place a heavy load on the disk because they are less likely to cause a starvation problem. For any particular list of requests, we can define an optimal order of retrieval, but the computation needed to find an optimal schedule may not justify the savings over SSTF or scan. With any scheduling algorithm, however, performance depends heavily on the number and types of requests. For instance, suppose that the queue usually has just one outstanding request. Then, all scheduling algorithms behave the same because they have only one choice of where to move the disk head. They all behave like FCFS scheduling. Requests for disk service can be greatly influenced by the file allocation method. A program reading a contiguously allocated file will generate several requests that are close together on the disk, resulting in limited head movement. A linked or indexed file, in contrast, may include blocks that are widely scattered on the disk, resulting in greater head movement. The location of directories and index blocks is also important. Since every file must be opened to be used, and opening a file requires searching the directory structure, the directories will be accessed frequently. Suppose that a directory entry is on the first cylinder and a file's data are on the final cylinder. In this case, the disk head has to move the entire width of the disk. If the directory entry were on the middle cylinder, the head would have to move only one-half the width. Caching the directories and index blocks in main memory can also help to reduce disk arm movement, particularly for read requests. Because of these complexities, the disk scheduling algorithm should be written as a separate module of the operating system so that it can be replaced with a different algorithm if necessary. Either SSTF or look is a reasonable choice for the default algorithm. The scheduling algorithms described here consider only the seek distances. For modern disks, the rotational latency can be nearly as large as the average seek time. It is difficult for the operating system to schedule for improved rotational latency though, because modern disks do not disclose the physical location of logical blocks. Disk manufacturers have been alleviating this problem by implementing disk scheduling algorithms in the controller hardware built into the disk drive. If the operating system sends a batch of requests to the controller can queue them and then schedule them to improve both the seek time and the rotational latency. If input-output performance were the only consideration, the operating system would gladly turn over the responsibility of disk scheduling to the disk hardware. In practice, however, the operating system may have other constraints on the service order for the requests. For instance, demand paging may take priority over application input-output, and writes are more urgent than reads if the cache is running out of free pages. Also, it may be desirable to guarantee the order of a set of disk writes to make the file system robust in the face of system crashes. Consider what could happen if the operating system allocated a disk page to a file and the application wrote data into that page before the operating system had a chance to flush the file system metadata back to disk. To accommodate such requirements, an operating system may choose to do its own disk scheduling and to spoon-feed the requests to the disk controller one by one for some types of input-output. Disk structure. Modern magnetic disk drives are addressed as large one-dimensional arrays of logical blocks, where the logical block is the smallest unit of transfer. The size of a logical block is usually 512 bytes, although some disks can be low-level formatted to have a different logical block size, such as 1024 bytes. The one-dimensional array of logical blocks is mapped onto the sectors of the disk sequentially. Sector 0 is the first sector of the first track on the outermost cylinder. The mapping proceeds in order through that track, then through the rest of the tracks in that cylinder, and then through the rest of the cylinders from outermost to innermost. By using this mapping, we can, at least in theory, convert a logical block number into an old-style disk address that consists of a cylinder number, a track number within that cylinder, and a sector number within that track. In practice, it is difficult to perform this translation for two reasons. First, most disks have some defective sectors, but the mapping hides this by substituting spare sectors from elsewhere on the disk. Second, the number of sectors per track is not a constant on some drives. Let's look more closely at the second reason. On media that use constant linear velocity (CLV), the density of bits per track is uniform. The farther a track is from the center of the disk, the greater its length, so the more sectors it can hold. As we move from outer zones to inner zones, the number of sectors per track decreases. Tracks in the outermost zone typically hold 40% more sectors than do tracks in the innermost zone. The drive increases its rotation speed as the head moves from the outer to the inner tracks to keep the same rate of data moving under the head. This method is used in CD-ROM and DVD-ROM drives. Alternatively, the disk rotation speed can stay constant. In this case, the density of bits decreases from inner tracks to outer tracks to keep the data rate constant. This method is used in hard disks and is known as constant angular velocity (CAV). The number of sectors per track has been increasing as disk technology improves, and the outer zone of a disk usually has several hundred sectors per track. Similarly, the number of cylinders per disk has been increasing. Large disks have tens of thousands of cylinders. File caching. By default, Windows caches file data that is read from disks and written to disks. This implies that read operations read file data from an area in system memory known as the system file cache rather than from the physical disk. Correspondingly, write operations write file data to the system file cache rather than to the disk, and this type of cache is referred to as a write-back cache. Caching is managed per file object. Caching occurs under the direction of the cache manager, which operates continuously while Windows is running. File data in the system file cache is written to the disk at intervals determined by the operating system, and the memory previously used by that file data is freed. This is referred to as flushing the cache. The policy of delaying the writing of the data to the file and holding it in the cache until the cache is flushed is called lazy writing, and it is triggered by the cache manager at a determinate time interval. The time at which a block of file data is flushed is partially based on the amount of time it has been stored in the cache and the amount of time since the data was last accessed in a read operation. This ensures that file data that is frequently read will stay accessible in the system file cache for the maximum amount of time. This file data caching process is illustrated in the following figure. As depicted by the solid arrows in the previous figure, a 256 KB region of data is read into a 256 KB cache slot in system address space when it is first requested by the cache manager during a file read operation. A user mode process then copies the data in this slot to its own address space. When the process has completed its data access, it writes the altered data back to the same slot in the system cache, as shown by the dotted arrow between the process address space and the system cache. When the cache manager has determined that the data will no longer be needed for a certain amount of time, it writes the altered data back to the file on the disk, as shown by the dotted arrow between the system cache and the disk. The amount of input-output performance improvement that file data caching offers depends on the size of the file data block being read or written. When large blocks of file data are read and written, it is more likely that the disk reads and writes will be necessary to finish the input-output operation. Input-output performance will be increasingly impaired as more of this kind of input-output operation occurs. In these situations, caching can be turned off. This is done at the time the file is opened by passing file_flag_no_buffering as a value for the DW flags and attributes parameter of create file. When caching is disabled, all read and write operations directly access the physical disk. However, the file metadata may still be cached. To flush the metadata to disk, use the flush file buffers function. The frequency at which flushing occurs is an important consideration that balances system performance with system reliability. If the system flushes the cache too often, the number of large write operations flushing incurs will degrade system performance significantly. If the system is not flushed often enough, then the likelihood is greater that either system memory will be depleted by the cache or a sudden system failure, such as a loss of power to the computer, will happen before the flush. In the latter instance, the cached data will be lost. To ensure that the right amount of flushing occurs, the cache manager spawns a process every second called a lazy writer. The lazy writer process queues 1/8 of the pages that have not been flushed recently to be written to disk. It constantly re-evaluates the amount of data being flushed for optimal system performance, and if more data needs to be written, it queues more data. Lazy writers do not flush temporary files because the assumption is that they will be deleted by the application or system. Some applications, such as virus checking software, require that their write operations be flushed to disk immediately. Windows provides this ability through write-through caching. A process enables write-through caching for a specific input-output operation by passing the file_flag_write_through flag into its call to create file. With write-through caching enabled, data is still written into the cache, but the cache manager writes the data immediately to disk rather than incurring a delay by using the lazy writer. A process can also force a flush of a file it has opened by calling the flush file buffers function. File system metadata is always cached. Therefore, to store any metadata changes to disk, the file must either be flushed or be opened with file_flag_write_through. File system formats: CDFS, FAT, NTFS, XFAT, etc. A file system is a means to organize data expected to be retained after a program terminates by providing procedures to store, retrieve and update data, as well as manage the available space in the device or devices which contain it. File system formats define the way the data file is stored on storage media and the way they affect a file system's structure. A file system organizes data in an efficient manner and is tuned to the specific characteristics of the device. File systems allocate space in a granular manner, usually multiple physical units on the device. The file system is responsible for organizing files and directories and keeping track of which areas of the media belong to which file and which are not being used. File systems formats: CD-ROM file system, CDFS. CD-ROM file system implemented in the Windows System32 drivers cdfs.systemfile or CDFS is a read-only file system driver that supports a superset of the ISO 9660 format as well as the superset of the Joliet disk format. While the ISO 9660 format is relatively simple and has limitations such as ASCII uppercase names with a maximum length of 32 characters, Joliet is more flexible and supports Unicode names of arbitrary length. If structures for both formats are present on a disk to offer maximum compatibility, CDFS uses the Joliet format. CDFS has a couple of restrictions: a maximum file size of 4 GB and a maximum of 65,535 directories. CDFS is a relatively simple format that was defined in 1988 as the read-only formatting standard for CD-ROM media. CDFS is considered a legacy format because the industry has adopted the Universal Disk Format (UDF) as the standard for optical media. Universal Disk Format (UDF). Universal Disk Format (UDF) is an implementation of the specification known as ISO IEC 13346 and ECMA 167 and is an open vendor neutral file system for computer data storage for a broad range of media. In practice, it has been most widely used for DVDs and newer optical disc formats, supplanting ISO 9660. Due to its design, it is very well suited for incremental updates on both recordable or rewritable optical media. UDF is developed and maintained by the Optical Storage Technology Association (OSTA). The Windows UDF driver implemented in the Windows System32 drivers udfs.systemfile supports UDF versions up to 2.60, providing read-write support for the DVD-RAM, CD-write or read-write, and DVD plus/minus write read-write drives when using UDF 2.50 and read-only support when using UDF 2.60. File Allocation Table (FAT). The File Allocation Table (FAT) file system is supported primarily to enable upgrades from previous versions of Windows for compatibility with other operating systems in multi-boot systems and as a format for flash drives or memory cards. The name of each FAT format includes a number that indicates the number of bits the format uses to identify clusters on a disk. The Windows FAT file system driver is implemented in the /Windows /System32 /drivers /fastfat.system file. FAT12's 12-bit cluster identifier limits a partition in storing a maximum of 2 to the power of 12, that is 4096 clusters. Windows uses cluster sizes from 512 bytes to 8 KB in size, which limits a FAT12 volume size to 32 MB. All FAT file system types reserve the first 2 clusters and the last 16 clusters of a volume, so the number of usable clusters for a FAT12 volume, for instance, is slightly less than 4096. FAT16 with a 16-bit cluster identifier can address 2 to the power of 16, that is 65,536 clusters. On Windows, FAT16 cluster sizes range from 512 bytes, the sector size, to 64 KB, which limits FAT16 volume sizes to 4 GB. The cluster size Windows uses depends on the size of a volume. If you format a volume that is less than 16 MB as FAT by using the format command or the Microsoft Management Console Disk Management snap-in, Windows uses the FAT12 format instead of FAT16. A FAT volume is divided into several regions. The file allocation table, which gives the FAT file system format its name, has one entry for each cluster on a volume. Because the file allocation table is critical to the successful interpretation of a volume's contents, the FAT format maintains 2 copies of the table so that if a file system driver or consistency checking program such as CHEDSK checkdisk can access one, because of a bad disk sector, for example, it can read from the other. FAT16 is an older file system. It was widely used on Windows NT 4.0 and provides optimal performance on volumes that are less than 2 GB. FAT32 is the version of FAT introduced with Windows 95 OEM Service Release 2 (OSR2) and Windows 98. FAT32 supports a 32-bit allocation table and supports smaller cluster sizes than FAT16 in order to more efficiently allocate space. FAT32 uses 32-bit cluster identifiers but reserves the high 4 bits, so in effect it has 28-bit cluster identifiers. Because FAT32 cluster sizes can be as large as 32 KB, FAT32 has a theoretical ability to address 8 terabyte TB volumes. Although Windows works with existing FAT32 volumes of larger sizes created in other operating systems, it limits new FAT32 volumes to a maximum of 32 GB. FAT32's higher potential cluster numbers let it manage disks more efficiently than FAT16. It can handle up to 128 GB volumes with 512-byte clusters. Besides the higher limit on cluster numbers, other advantages FAT32 has over FAT12 and FAT16 include the fact that the FAT32 root directory isn't stored at a predefined location on the volume. The root directory doesn't have an upper limit on its size, and FAT32 stores a second copy of the boot sector for reliability. A limitation FAT32 shares with FAT16 is that the maximum file size is 4 GB because directories store file sizes as 32-bit values. Extended File Allocation Table (XFAT). Designed by Microsoft, the Extended File Allocation Table file system (XFAT), also called FAT64, is an improvement over the traditional FAT file systems and is specifically designed for flash drives. The main goal of XFAT is to provide some of the advanced functionality offered by NTFS, but without the metadata structure overhead and metadata logging that create write patterns not suited for many flash media devices. As the FAT64 name implies, the file size limit is increased to 2 to the power 64, allowing files up to 16 exabytes. This change is also matched by an increase in the maximum cluster size, which is currently implemented as 32 MB but can be as large as 2 to the power of 255 sectors. exFAT also adds a bitmap that tracks free clusters, which improves the performance of allocation and deletion operations. Finally, exFAT allows more than 1000 files in a single directory. These characteristics result in increased scalability and support for large disk sizes. Additional exFAT implements certain features previously available only in NTFS, such as support for access control lists, ACLs, and transactions called transaction-safe FAT or TFAT. The exFAT file system is implemented in the /Windows /system32 /drivers /exFAT.system file. New Technology File System NTFS. New Technology File System implemented in the Windows System32 Drivers NTFS.system file or NTFS is the native file system format of Windows. NTFS uses 64-bit cluster numbers and can address volumes of up to 16-bit clusters. However, Windows limits the size of an NTFS volume to that addressable with 32-bit clusters, which is slightly less than 256 terabyte. Using 64 KB clusters, you can override the default when you format an NTFS volume. NTFS also supports 2 to the power of 32-1 files per volume. The NTFS format allows for files that are 16 exabytes. The exabyte is the multiplication of 6th power of 1000, that is, 1000 to the power of 6 in size, but the implementation limits the maximum file size to 16 terabytes. The NTFS includes a number of advanced features such as file and directory security, alternate data streams, disk quotas, sparse files, file compression, symbolic, soft, and hard links, support for transactional semantics, and encryption. One of its most significant features is recoverability. If a system is halted unexpectedly, the metadata of a FAT volume can be left in an inconsistent state, leading to the corruption of large amounts of file and directory data. NTFS logs changes to metadata in a transactional manner so that file system structures can be repaired to a consistent state with no loss of file or directory structure information. File data can be lost, however. Additionally, the NTFS driver in Windows also implements self-healing, a mechanism through which it makes most minor repairs to corruption of file system on disk structures while Windows is running and without requiring a reboot. Input-output hardware. Computers operate a great many kinds of devices. Most fit into the general categories of storage devices, disks, tapes, transmission devices, network cards, modems, and human interface devices, screen, keyboard, mouse. Other devices are more specialized, such as the steering of a military fighter jet or a space shuttle. In these aircraft, a human gives input to the flight computer via a joystick and foot pedals, and the computer sends output commands that cause motors to move rudders, flaps, and thrusters. Despite the incredible variety of input-output devices, though, we need only a few concepts to understand how the devices are attached and how the software can control the hardware. A device communicates with a computer system by sending signals over a cable or even through the air. The device communicates with the machine via a connection point or port, for example, a serial port. If devices use a common set of wires, the connection is called a bus. A bus is a set of wires and a rigidly defined protocol that specifies a set of messages that can be sent on the wires. In terms of the electronics, the messages are conveyed by patterns of electrical voltages applied to the wires with defined timings. When device A has a cable that plugs into device B, and the device B has a cable that plugs into device C, and device C plugs into a port on the computer, this arrangement is called a daisy chain. A daisy chain usually operates as a bus. Buses are used widely in computer architecture and vary in their signaling methods, speed, throughput, and connection methods. A typical PC bus structure appears in figure below. In the figure, a PCI bus, the common PC system bus, connects the processor, memory subsystem to fast devices, and an expansion bus connects relatively slow devices such as the keyboard and serial and USB ports. In the upper right portion of the figure, 4 disks are connected together on a small computer system interface SCSI bus plugged into a SCSI controller. Other common buses used to interconnect main parts of a computer include PCI Express PCIe with throughput of up to 16 GB per second and Hyper Transport with throughput of up to 25 GB per second. A controller is a collection of electronics that can operate a port, a bus, or a device. A serial port controller is a simple device controller. It is a single chip or portion of a chip in the computer that controls the signals on the wires of a serial port. By contrast, a SCSI bus controller is not simple. Because the SCSI protocol is complex, the SCSI bus controller is often implemented as a separate circuit board or a host adapter that plugs into the computer. It typically contains a processor, microcode, and some private memory to enable it to process the SCSI protocol messages. Some devices have their own built-in controllers. If you look at a disk drive, you will see a circuit board attached to one side. This board is a disk controller. It implements the disk side of the protocol for some kind of connection, SCSI or Serial Advanced Technology Attachment, SATA for instance. It has microcode and a processor to do many tasks such as bad sector mapping, prefetching, buffering, and caching. How can the processor give commands and data to a controller to accomplish an input-output transfer? The short answer is that the controller has one or more registers for data and control signals. The processor communicates with the controller by reading and writing bit patterns in these registers. One way in which this communication can occur is through the use of special input-output instructions that specify the transfer of a byte or word to an input-output port address. The input-output instruction triggers bus lines to select the proper device and to move bits into or out of a device register. Alternatively, the device controller can support memory-mapped input-output. In this case, the device control registers are mapped into the address space of the processor. The CPU executes input-output requests using the standard data transfer instructions to read and write the device control registers at their mapped locations in physical memory. Some systems use both techniques. For instance, PCs use input-output instructions to control some devices and memory-mapped input-output to control others. Figure shows the usual input-output port addresses for PCs. The graphics controller has input-output ports for basic control operations, but the controller has a large memory-mapped region to hold screen contents. The process sends output to the screen by writing data into the memory-mapped region. The controller generates the screen image based on the contents of this memory. This technique is simple to use. Moreover, writing millions of bytes to the graphics memory is faster than using millions of input-output instructions. But the ease of writing to a memory-mapped input-output controller is offset by a disadvantage. Because a common type of software fault is a write through an incorrect pointer to an unintended region of memory, a memory-mapped device register is vulnerable to accidental modification. Of course, protected memory helps to reduce this risk. An input-output port typically consists of 4 registers called the status, control, data in, and data out registers. The data in register is read by the host to get input. The data out register is written by the host to send output. The status register contains bits that can be read by the host. These bits indicate states such as whether the current command has completed, whether a byte is available to be read from the data in register, and whether a device error has occurred. The control register can be written by the host to start a command or to change the mode of a device. For instance, a certain bit in the control register of a serial port chooses between full duplex and half duplex communication, another bit enables parity checking, a third bit sets a word length to 7 or 8 bits, and other bits select one of the speeds supported by the serial port. The data registers are typically 1 to 4 bytes in size. Some controllers have 5/4 chips that can hold several bytes of input or output data to expand the capacity of the controller beyond the size of the data register. A 5/4 chip can hold a small burst of data until the device or host is able to receive those data. Polling. The complete protocol for interaction between the host and a controller can be intricate, but the basic handshaking notion is simple. We explain handshaking with an example. Assume that 2 bits are used to coordinate the producer-consumer relationship between the controller and the host. The controller indicates its state through the busy bit in the status register. Recall that to set a bit means to write a 1 into the bit, and to clear a bit means to write a 0 into it. The controller sets the busy bit when it is busy working and clears the busy bit when it is ready to accept the next command. The host signals its wishes via the command ready bit in the command register. The host sets the command ready bit when a command is available for the controller to execute. For this example, the host writes output through a port, coordinating with the controller by handshaking as follows. The host repeatedly reads the busy bit until that bit becomes clear. The host sets the write bit in the command register and writes a byte into the data out register. The host sets the command ready bit. When the controller notices that the command ready bit is set, it sets the busy bit. The controller reads the command register and sees the write command. It reads the data out register to get the byte and does the input-output to the device. A controller clears the command ready bit, clears the error bit in the status register to indicate that the device input-output succeeded, and clears the busy bit to indicate that it is finished. This loop is repeated for each byte. In step 1, the host is busy waiting or polling. It is in a loop, reading the status register over and over until the busy bit becomes clear. If the controller and device are fast, this method is a reasonable one. But if the wait may be long, the host should probably switch to another task. How then does the host know when the controller has become idle? For some devices, the host must service the device quickly or data will be lost. For instance, when data are streaming in on a serial port or from a keyboard, the small buffer on the controller will overflow and data will be lost if the host waits too long before returning to read the bytes. In many computer architectures, 3 CPU instruction cycles are sufficient to poll a device, read a device register, logical, and to extract a status bit and branch if not 0. Clearly, the basic polling operation is efficient, but polling becomes inefficient when it is attempted repeatedly yet rarely finds a device ready for service, while other useful CPU processing remains undone. In such instances, it may be more efficient to arrange for the hardware controller to notify the CPU when the device becomes ready for service, rather than to require the CPU to poll repeatedly for an input-output completion. The hardware mechanism that enables a device to notify the CPU is called an interrupt. Interrupts. The basic interrupt mechanism works as follows. The CPU hardware has a wire called the interrupt request line that the CPU senses after executing every instruction. When the CPU detects that a controller has asserted a signal on the interrupt request line, the CPU performs a state save and jumps into the interrupt handler routine at a fixed address in memory. The interrupt handler determines the cause of the interrupt, performs the necessary processing, performs a state restore, and executes a return from interrupt instruction to return the CPU to the execution state prior to the interrupt. We say that the device controller raises an interrupt by asserting a signal on the interrupt request line. The CPU catches the interrupt and dispatches it to the interrupt handler, and the handler clears the interrupt by servicing the device. Figure summarizes the interrupt-driven input-output cycle. We stress interrupt management in this chapter because even single-user modern systems manage hundreds of interrupts per second and service hundreds of thousands per second. The basic interrupt mechanism just described enables the CPU to respond to an asynchronous event as when a device controller becomes ready for service. In a modern operating system, however, we need more sophisticated interrupt handling features. We need the ability to defer interrupt handling during critical processing. We need an efficient way to dispatch to the proper interrupt handler for a device without first polling all the devices to see which one raised the interrupt. We need multi-level interrupts so that the operating system can distinguish between high and low priority interrupts and can respond with the appropriate degree of urgency. In modern computer hardware, these three features are provided by the CPU and by the interrupt controller hardware. Most CPUs have two interrupt request lines. One is the non-maskable interrupt, which is reserved for events such as unrecoverable memory errors. The second interrupt line is maskable. It can be turned off by the CPU before the execution of critical instruction sequences that must not be interrupted. The maskable interrupt is used by device controllers to request service. The interrupt mechanism accepts an address, a number that selects a specific interrupt handling routine from a small set. In most architectures, this address is an offset in a table called the interrupt vector. This vector contains the memory addresses of specialized interrupt handlers. The purpose of a vectored interrupt mechanism is to reduce the need for a single interrupt handler to search all possible sources of interrupts to determine which one needs service. In practice, however, computers have more devices and hence interrupt handlers than they have address elements in the interrupt vector. A common way to solve this problem is to use interrupt chaining, in which each element in the interrupt vector points to the head of a list of interrupt handlers. When an interrupt is raised, the handlers on the corresponding list are called one by one until one is found that can service the request. This structure is a compromise between the overhead of a huge interrupt table and the inefficiency of dispatching to a single interrupt handler. Figure illustrates the design of the interrupt vector for the Intel Pentium processor. The events from 0 to 31, which are non-maskable, are used to signal various error conditions. The events from 32 to 255, which are maskable, are used for purposes such as device-generated interrupts. The interrupt mechanism also implements a system of interrupt priority levels. These levels enable the CPU to defer the handling of low-priority interrupts without masking all interrupts and makes it possible for a high-priority interrupt to preempt the execution of a low-priority interrupt. A modern operating system interacts with the interrupt mechanism in several ways. At boot time, the operating system probes the hardware buses to determine what devices are present and installs the corresponding interrupt handlers into the interrupt vector. During input-output, the various device controllers raise interrupts when they are ready for service. These interrupts signify that output has completed, or that input data are available, or that a failure has been detected. The interrupt mechanism is also used to handle a wide variety of exceptions, such as dividing by zero, accessing a protected or non-existent memory address, or attempting to execute a privileged instruction from user mode. The events that trigger interrupts have a common property. They are occurrences that induce the operating system to execute an urgent, self-contained routine. An operating system has other good uses for an efficient hardware and software mechanism that saves a small amount of processor state and then calls a privileged routine in the kernel. For example, many operating systems use the interrupt mechanism for virtual memory paging. A page fault is an execution that raises an interrupt. The interrupt suspends the current process and jumps to the page fault handler in the kernel. This handler saves the state of the process, moves the process to the wait queue, performs the page cache management, schedules an input-output operation to fetch the page, schedules another process to resume execution, and then returns from the interrupt. Another example is found in the implementation of system calls. Usually, a program uses library calls to issue system calls. The library routines check the arguments given by the application, build a data structure to convey the arguments to the kernel, and then execute a special instruction called a software interrupt or trap. This instruction has an operand that identifies the desired kernel service. When a process executes the trap instruction, the interrupt hardware saves the state of the user code, switches to kernel mode, and dispatches to the kernel routine that implements the requested service. The trap is given a relatively low interrupt priority compared with those assigned to device interrupts. Executing a system call on behalf of an application is less urgent than servicing a device controller before its FIFO queue overflows and loses data. Interrupts can also be used to manage the flow of control within the kernel. For example, consider one example of the processing required to complete a disk read. One step is to copy data from kernel space to the user buffer. This copying is time-consuming but not urgent. It should not block other high-priority interrupt handling. Another step is to start the next pending input-output for that disk drive. This step has higher priority. If the disks are to be used efficiently, we need to start the next input-output as soon as the previous one completes. Consequently, a pair of interrupt handlers implements the kernel code that completes a disk read. The higher priority handler records the input-output status, clears the device interrupt, starts the next pending input-output, and raises a low priority interrupt to complete the work. Later, when the CPU is not occupied with high priority work, the low priority interrupt will be dispatched. The corresponding handler completes the user-level input-output by copying data from kernel buffers to the application space and then calling the scheduler to place the application on the ready queue. A threaded kernel architecture is well suited to implement multiple interrupt priorities and to enforce the precedence of interrupt handling over background processing in kernel and application routines. We illustrate this point with the Solaris kernel. In Solaris, interrupt handlers are executed as kernel threads. A range of high priorities is reserved for these threads. These priorities give interrupt handlers precedence over application code and kernel housekeeping and implement the priority relationships among interrupt handlers. The priorities cause the Solaris threads scheduler to preempt low priority interrupt handlers in favor of higher priority ones, and the threaded implementation enables multiprocessor hardware to run several interrupt handlers concurrently. We described the interrupt architecture of Windows XP and Unix in Chapter 19 and Appendix A, respectively. In summary, interrupts are used throughout modern operating systems to handle asynchronous events and to trap the supervisor mode routines in the kernel. To enable the most urgent work to be done first, modern computers use a system of interrupt priorities. Device controllers, hardware faults, and system calls all raise interrupts to trigger kernel routines. Because interrupts are used so heavily for time-sensitive processing, efficient interrupt handling is required for good system performance. Direct memory access. For a device that does large transfers, such as a disk drive, it seems wasteful to use an expensive general-purpose processor to watch status bits and to feed data into a controller register 1 byte at a time, a process termed Programmed Input-Output (PIO). Many computers avoid burdening the main CPU with PIO by offloading some of this work to a special-purpose processor called a Direct Memory Access (DMA) controller. To initiate a DMA transfer, the host writes a DMA command block into memory. This block contains a pointer to the source of a transfer, a pointer to the destination of the transfer, and a count of the number of bytes to be transferred. The CPU writes the address of this command block to the DMA controller, then goes on with other work. The DMA controller proceeds to operate the memory bus directly, placing addresses on the bus to perform transfers without the help of the main CPU. A simple DMA controller is a standard component in all modern computers, from smartphones to mainframes. Handshaking between the DMA controller and the device controller is performed via a pair of wires called DMA request and DMA acknowledge. The device controller places a signal on the DMA request wire when a word of data is available for transfer. The signal causes the DMA controller to seize the memory bus, place the desired address on the memory address wires, and place a signal on the DMA acknowledge wire. When the device controller receives the DMA acknowledge signal, it transfers the word of data to memory and removes the DMA request signal. When the entire transfer is finished, the DMA controller interrupts the CPU. This process is depicted in figure below, Steps in a DMA transfer. When the DMA controller seizes the memory bus, the CPU is momentarily prevented from accessing main memory. Although it can still access data items in its primary and secondary caches. Although this cycle stealing can slow down the CPU computation, offloading the data transfer work to a DMA controller generally improves the total system performance. Some computer architectures use physical memory addresses for DMA, but others perform Direct Virtual Memory Access (DVMA). Using virtual addresses that undergo translation to physical addresses. DVMA can perform a transfer between two memory-mapped devices without the intervention of the CPU or the use of main memory. On protected mode kernels, the operating system generally prevents processes from issuing device commands directly. This discipline protects data from access control violations and also protects the system from erroneous use of device controllers that could cause a system crash. Instead, the operating system exports functions that a sufficiently privileged process can use to access low-level operations on the underlying hardware. On kernels without memory protection, processes can access device controllers directly. This direct access can be used to achieve high performance since it can avoid kernel communication, context switches, and layers of kernel software. Unfortunately, it interferes with system security and stability. The trend in general-purpose operating systems is to protect memory and devices so that the system can try to guard against erroneous or malicious applications. Input-output hardware summary. Although the hardware aspects of input-output are complex when considered at the level of detail of electronics hardware design, the concepts that we have just described are sufficient to enable us to understand many input-output features of operating systems. Let's review the main concepts: a bus, a controller, an input-output port and its registers, the handshaking relationship between the host and a device controller, the execution of this handshaking in a polling loop or via interrupts, the offloading of this work to a DMA controller for large transfers. We gave a basic example of the handshaking that takes place between a device controller and the host earlier in this section. In reality, the wide variety of available devices poses a problem for operating system implementers. Each kind of device has its own set of capabilities, control bit definitions, and protocols for interacting with the host, and they are all different. How can the operating system be designed so that we can attach new devices to the computer without rewriting the operating system? And when the devices vary so widely, how can the operating system give a convenient, uniform input-output interface to applications? We address those questions next. Input-output systems. The two main jobs of a computer are input, output, and processing. In many cases, the main job is input-output, and the processing is merely incidental. For instance, when we browse a web page or edit a file, our immediate interest is to read or enter some information, not to compute an answer. The role of the operating system in computer input-output is to manage and control input-output operations and input-output devices. Although related topics appear in other chapters, here we bring together the pieces to paint a complete picture of input-output. First, we describe the basics of input-output hardware because the nature of the hardware interface places requirements on the internal facilities of the operating system. Next, we discuss the input-output services provided by the operating system and the embodiment of these services in the application input-output interface. Then, we explain how the operating system bridges the gap between the hardware interface and the application interface. We also discuss the UM1X system vStreams mechanism, which enables an application to assemble pipelines of driver code dynamically. Finally, we discuss the performance aspects of input-output and the principles of operating system design that improve input-output performance. Overview. The controller devices connected to the computer is a major concern of operating system designers because input-output devices vary so widely in their function and speed. Consider a mouse, a hard disk, and a CD-ROM jukebox. Varied methods are needed to control them. These methods form the input-output subsystem of the kernel, which separates the rest of the kernel from the complexities of managing input-output devices. Input-output device technology exhibits two conflicting trends. On one hand, we see increasing standardization of software and hardware interfaces. This trend helps us to incorporate improved device generations into existing computers and operating systems. On the other hand, we see an increasingly broad variety of input-output devices. Some new devices are so unlike previous devices that it is a challenge to incorporate them into our computers and operating systems. This challenge is met by a combination of hardware and software techniques. The basic input-output hardware elements, such as ports, buses, and device controllers, accommodate a wide variety of input-output devices. To encapsulate the details and oddities of different devices, the kernel of an operating system is structured to use device driver modules. The device drivers present a uniform device access interface to the input-output subsystem, much as system calls provide a standard interface between the application and the operating system. Kernel input-output subsystem. Kernels provide many services related to input-output. Several services, scheduling, buffering, caching, spooling, device reservation and error handling, are provided by the kernel's input-output subsystem and built on the hardware and device driver infrastructure. The input-output subsystem is also responsible for protecting itself from errant processes and malicious users. Input-output scheduling. To schedule a set of input-output requests means to determine a good order in which to execute them. The order in which applications issue system calls rarely is the best choice. Scheduling can improve overall system performance, can share device access fairly among processes, and can reduce the average waiting time for input-output to complete. Here is a simple example to illustrate. Suppose that a disk arm is near the beginning of a disk and that 3 applications issue blocking read calls to that disk. Application 1 requests a block near the end of the disk, Application 2 requests one near the beginning, and Application 3 requests one in the middle of the disk. The operating system can reduce the distance that the disk arm travels by serving the applications in the order 2, 3, 1. Rearranging the order of service in this way is the essence of input-output scheduling. Operating system developers implement scheduling by maintaining a wait queue of requests for each device. When an application issues a blocking input-output system call, the request is placed on the queue for that device. The input-output scheduler rearranges the order of the queue to improve the overall system efficiency and the average response time experienced by applications. The operating system may also try to be fair so that no one application receives especially poor service, or it may give priority service for delay-sensitive requests. For instance, requests from the virtual memory subsystem may take priority over application requests. When a kernel supports asynchronous input-output, it must be able to keep track of many input-output requests at the same time. For this purpose, the operating system might attach the wait queue to a device status table. The kernel manages this table, which contains an entry for each input-output device as shown in figure below. Each table entry indicates the device's type, address, and state, not functioning, idle, or busy. If the device is busy with a request, the type of request and other parameters will be stored in the table entry for that device. Scheduling input-output operations is one way in which the input-output subsystem improves the efficiency of the computer. Another way is by using storage space in main memory or on disk via buffering, caching, and spooling. Buffering. A buffer, of course, is a memory area that stores data being transferred between two devices or between a device and an application. Buffering is done for 3 reasons. One reason is to cope with the speed mismatch between the producer and consumer of a data stream. Suppose, for example, that a file is being received via modem for storage on the hard disk. The modem is about 1,000 times slower than the hard disk, so a buffer is created in main memory to accumulate the bytes received from the modem. When an entire buffer of data has arrived, the buffer can be returned to disk in a single operation. Since the disk write is not instantaneous and the modem still needs a place to store additional incoming data, 2 buffers are used. After the modem fills the first buffer, the disk write is requested. The modem then starts to fill the second buffer while the first buffer is written to disk. By the time the modem has filled the second buffer, the disk write from the first one should have completed, so the modem can switch back to the first buffer while the disk writes the second one. This double buffering decouples the producer of data from the consumer, thus relaxing timing requirements between them. The need for this decoupling is illustrated in figure below. Sun Enterprise 6000 device transfer rates, logarithmic, which lists the enormous differences in device speeds for typical computer hardware. A second use of buffering is to provide adaptations for devices that have different data transfer sizes. Such disparities are especially common in computer networking, where buffers are used widely for fragmentation and reassembly of messages. At the sending side, a large message is fragmented into small network packets. The packets are sent over the network and the receiving side places them in a reassembly buffer to form an image of the source data. A third use of buffering is to support copy semantics for application input-output. An example will clarify the meaning of copy semantics. Suppose that an application has a buffer of data that it wishes to write to disk. It calls the write function system call, providing a pointer to the buffer and an integer specifying the number of bytes to write. After the system call returns, what happens if the application changes the contents of the buffer? With copy semantics, the version of the data written to disk is guaranteed to be the version at the time of the application system call, independent of any subsequent changes in the application's buffer. A simple way in which the operating system can guarantee copy semantics is for the write function system call to occupy the application data into a kernel buffer before returning control to the application. The disk write is performed from the kernel buffer so that subsequent changes to the application buffer have no effect. Copying of data between kernel buffers and application data space is common in operating systems, despite the overhead that this operation introduces because of the clean semantics. The same effect can be obtained more efficiently by clever use of virtual memory mapping and copy-on-write page protection. Caching. A cache is a region of fast memory that holds copies of data. Access to the cached copy is more efficient than access to the original. For instance, the instructions of the currently running process are stored on disk, cached in physical memory, and copied again in the CPU's secondary and primary caches. The difference between a buffer and a cache is that a buffer may hold the only existing copy of a data item, whereas a cache, by definition, holds a copy on faster storage of an item that resides elsewhere. Caching and buffering are distinct functions, but sometimes a region of memory can be used for both purposes. For instance, to preserve copy semantics and to enable efficient scheduling of the disk input-output, the operating system uses buffers in main memory to hold disk data. These buffers are also used as a cache to improve the input-output efficiency for files that are shared by applications or that are being written and reread rapidly. When the kernel receives a file input-output request, the kernel first accesses the buffer cache to see whether that region of the file is already available in main memory. If it is, a physical disk input-output can be avoided or deferred. Also, disk writes are accumulated in the buffer cache for several seconds so that large transfers are gathered to allow efficient write schedules. This strategy of delaying writes to improve input-output efficiency. Spooling and device reservation. A spool is a buffer that holds output for a device, such as a printer, that cannot accept interleaved data streams. Although a printer can serve only one job at a time, several applications may wish to print their output concurrently without having their output mixed together. The operating system solves this problem by intercepting all output to the printer. Each application's output is spooled to a separate disk file. When an application finishes printing, the spooling system queues the corresponding spool file for output to the printer. The spooling system copies the queued spool files to the printer one at a time. In some operating systems, spooling is managed by a system daemon process. In others, it is handled by an in-kernel thread. In either case, the operating system provides a control interface that enables users and system administrators to display the queue, remove unwanted jobs before those job print, suspend printing while the printer is serviced, and so on. Some devices, such as tape drives and printers, cannot usefully multiplex the input-output requests of multiple concurrent applications. Spooling is one way operating systems can coordinate concurrent output. Another way to deal with concurrent device access is to provide explicit facilities for coordination. Some operating systems, including VMS, provide support for exclusive device access by enabling a process to allocate an idle device and to deallocate that device when it is no longer needed. Other operating systems enforce a limit of one open file handle to such a device. Many operating systems provide functions that enable processes to coordinate exclusive access among themselves. For instance, Windows provides system calls to wait until a device object becomes available. It also has a parameter to the OpenFile function system call that declares the types of access to be permitted to other concurrent threads. On these systems, it is up to the applications to avoid deadlock. Error handling. An operating system that uses protected memory can guard against many kinds of hardware and application errors so that a complete system failure is not the usual result of each minor mechanical malfunction. Devices and input-output transfers can fail in many ways, either for transient reasons as when a network becomes overloaded or for permanent reasons as when a disk controller becomes defective. Operating systems can often compensate effectively for transient failures. For instance, a disk read function failure results in a read function retry, and a network send function error results in a resend function if the protocol so specifies. Unfortunately, if an important component experiences a permanent failure, the operating system is unlikely to recover. As a general rule, an input-output system call will return one bit of information about the status of the call, signifying either success or failure. In the Unix operating system, an additional integer variable named ERR number is used to return an error code, one of about 100 values, indicating the general nature of the failure, for example, argument out of range, bad pointer, or file not open. By contrast, some hardware can provide highly detailed error information, although many current operating systems are not designed to convey this information to the application. For instance, a failure of a SCSI device is reported by the SCSI protocol in 3 levels of detail: a sense key that identifies the general nature of the failure, such as a hardware error or an illegal request; an additional sense code that states the category of failure, such as a bad command parameter or a self-test failure; and an additional sense code qualifier that gives even more detail, such as which command parameter was in error or which hardware system failed its self-test. Further, many SCSI devices maintain internal pages of error log information that can be requested by the host but seldom are. Input-output protection. Errors are closely related to the issue of protection. A user process may accidentally or purposely attempt to disrupt the normal operation of a system by attempting to issue illegal input-output instructions. We can use various mechanisms to ensure that such disruptions cannot take place in the system. To prevent users from performing illegal input-output, we define all input-output instructions to be privileged instructions. Thus, users cannot issue input-output instructions directly. They must do it through the operating system. To do input-output, a user program executes a system call to request that the operating system perform input-output on its behalf. Figure below depicts use of system call to perform input-output. The operating system executing in monitor mode checks that the request is valid and, if it is, does the input-output requested. The operating system then returns to the user. In addition, any memory-mapped and input-output port memory locations must be protected from user access by the memory protection system. Note that a kernel cannot simply deny all user access. Most graphics, games, and video editing and playback software need direct access to memory-mapped graphics controller memory to speed the performance of the graphics, for example. The kernel might in this case provide a locking mechanism to allow a section of graphics memory representing a window on screen to be allocated to one process at a time. Kernel data structures. The kernel needs to keep state information about the use of input-output components. It does so through a variety of in-kernel data structures such as the open file table structure. The kernel uses many similar structures to track network connections, character-device communications, and other input-output activities. Unix provides file system access to a variety of entities such as user files, raw devices, and the address spaces of processes. Although each of these entities supports a read function operation, the semantics differ. For instance, to read a user file, the kernel needs to probe the buffer cache before deciding whether to perform a disk input-output. To read a raw disk, the kernel needs to ensure that the request size is a multiple of the disk sector size and is aligned on a sector boundary. To read a process image, it is merely necessary to copy data from memory. Unix encapsulates these differences within a uniform structure by using an object-oriented technique. Kernel data structures. The open file record, shown in figure below, Unix input-output kernel structure, contains a dispatch table that holds pointers to the appropriate routines depending on the type of file. Some operating systems use object-oriented methods even more extensively. For instance, Windows uses a message passing implementation for input-output. An input-output request is converted into a message that is sent through the kernel to the input-output manager and then to the device driver, each of which may change the message contents. For output, the message contains the data to be written. For input, the message contains a buffer to receive the data. The message passing approach can add overhead by comparison with procedural techniques that use shared data structures, but it simplifies the structure and design of the input-output system and adds flexibility. Kernel input-output subsystem summary. In summary, the input-output subsystem coordinates an extensive collection of services that are available to applications and to other parts of the kernel. The input-output subsystem supervises these procedures: management of the namespace for files and devices, access control to files and devices, operation control, for example, a modem cannot seek function, file system space allocation, device allocation, buffering, caching and spooling, input-output scheduling, device status monitoring, error handling and failure recovery, device driver configuration and initialization. The upper levels of the input-output subsystem access devices via the uniform interface provided by the device drivers. Kernel mode and user mode driver framework. A processor in a computer running Windows has two different modes, user mode and kernel mode. The processor switches between the two modes depending on what type of code is running on the processor. Applications run in user mode and core operating system components run in kernel mode. While many drivers run in kernel mode, some drivers may run in user mode. When you start a user mode application, Windows creates a process for the application. The process provides the application with a private virtual address space and a private handle table. Because an application's virtual address space is private, one application cannot alter data that belongs to another application. Each application runs in isolation, and if an application crashes, the crash is limited to that one application. Other applications and the operating system are not affected by the crash. In addition to being private, the virtual address space of a user mode application is limited. A processor running in user mode cannot access virtual addresses that are reserved for the operating system. Limiting the virtual address space of a user mode application prevents the application from altering and possibly damaging critical operating system data. All code that runs in kernel mode shares a single virtual address space. This means that a kernel mode driver is not isolated from other drivers and the operating system itself. If a kernel mode driver accidentally writes to the wrong virtual address, data that belongs to the operating system or another driver could be compromised. If a kernel mode driver crashes, the entire operating system crashes. This diagram illustrates communication between user mode and kernel mode components. Performance issues file system. File system performance is often a major component of overall system performance and is heavily dependent on the nature of the application generating the load. To achieve optimal performance, the underlying file system configuration must be balanced to match the application characteristics. If you are a developer, then you may already have a good idea of how your application is reading or writing through the file system. But if you are an administrator of an application, then you may need to spend some time analyzing the application to understand what type of input-output profile is being presented to the file system. Once we have a good understanding of the application, we can try and optimize the file system configuration to make the most efficient use of the underlying storage device. Our objective is to reduce the number of input outputs to the underlying device or devices where possible, group smaller input outputs together into larger input outputs where possible, optimize the seek pattern to reduce the amount of time spent waiting for disk seeks, cache as much as data as realistic to reduce physical input outputs. We will only touch on file system caching this month and leave the bulk of Solaris caching implementation to the next month. Performance. Input-output is a major factor in system performance. It places heavy demands on the CPU to execute device driver code and to schedule processes fairly and efficiently as they block and unblock. The resulting context switches stress the CPU and its hardware caches. Input-output also exposes any inefficiencies in the interrupt handling mechanisms in the kernel. In addition, input-output loads down the memory bus during data copies between controllers and physical memory, and again during copies between kernel buffers and application data space. Coping gracefully with all these demands is one of the major concerns of a computer architect. Although modern computers can handle many thousands of interrupts per second, interrupt handling is a relatively expensive task. Each interrupt causes the system to perform a state change, to execute the interrupt handler, and then to restore state. Programmed input-output can be more efficient than interrupt-driven input-output if the number of cycles spent in busy waiting is not excessive. An input-output completion typically unblocks a process, leading to the full overhead of a context switch. Network traffic can also cause a high context switch rate. Consider, for instance, a remote login from one machine to another. Each character typed on the local machine must be transported to the remote machine. On the local machine, the character is typed. A keyboard interrupt is generated, and the character is passed through the interrupt handler to the device driver, to the kernel, and then to the user process. The user process issues a network input-output system call to send the character to the remote machine. The character then flows into the local kernel through the network layers that construct a network packet and into the network device driver. The network device driver transfers the packet to the network controller, which sends the character and generates an interrupt. The interrupt is passed back up through the kernel to cause the network input-output system call to complete. Now the remote system's network hardware receives the packet and an interrupt is generated. The character is unpacked from the network protocols and is given to the appropriate network daemon. The network daemon identifies which remote login session is involved and passes the packet to the appropriate subdaemon for that session. Throughout this flow, there are context switches and state switches. Figure below shows intercomputer communications. Usually the receiver echoes the character back to the sender. That approach doubles the work. To eliminate the context switches involved in moving each character between daemons and the kernel, the Solaris developers re-implemented the telnet daemon using in-kernel threads. Sun estimated that this improvement increased the maximum number of network logins from a few hundred to a few thousand on a large server. Other systems use separate front-end processes for terminal input-output to reduce the interrupt burden on the main CPU. For instance, a terminal concentrator can multiplex the traffic from hundreds of remote terminals into one port on a large computer. An input-output channel is dedicated, special-purpose CPU found in mainframes and in other high-end systems. The job of a channel is to offload input-output work from the main CPU. The idea is that the channels keep the data flowing smoothly while the main CPU remains free to process the data. Like the device controllers and DMA controllers found in smaller computers, a channel can process more general and sophisticated programs, so channels can be tuned for particular workloads. We can employ several principles to improve the efficiency of input-output. Reduce the number of context switches. Reduce the number of times that data must be copied in memory while passing between device and application. Reduce the frequency of interrupts by using large transfers, smart controllers, and polling if busy waiting can be minimized. Increase concurrency by using DMA-knowledgeable controllers or channels to offload simple data copying from the CPU. Move processing primitives into hardware to allow their operation and device controllers to be concurrent with CPU and bus operation. Balance CPU, memory subsystem, bus, and input-output performance because an overload in any one area will cause idleness in others. Input-output devices vary greatly in complexity. For instance, a mouse is simple. The mouse movements and button clicks are converted into numeric values that are passed from hardware through the mouse device driver to the application. By contrast, the functionality provided by the Windows disk device driver is complex. It not only manages individual disks but also implements RAID arrays. To do so, it converts an application's read or write request into a coordinated set of disk input-output operations. Moreover, it implements sophisticated error handling and data recovery algorithms and takes many steps to optimize disk performance. Where should the input-output functionality be implemented? In the device hardware, in the device driver, or in application software? Sometimes we observe the progression depicted in figure, device functionality progression. Initially, we implement experimental input-output algorithms at the application level because application code is flexible and application bugs are unlikely to cause system crashes. Furthermore, by developing code at the application level, we avoid the need to reboot or reload device drivers after every change to the code. An application-level implementation can be inefficient, however, because of the overhead of context switches and because the application cannot take advantage of internal kernel data structures and kernel functionality, such as efficient in kernel messaging, threading, and locking. When an application-level algorithm has demonstrated its worth, we may re-implement it in the kernel. This can improve performance, but the development effort is more challenging because an operating system kernel is a large, complex software system. Moreover, an in-kernel implementation must be thoroughly debugged to avoid data corruption and system crashes. The highest performance may be obtained through a specialized implementation in hardware, either in the device or in the controller. The disadvantages of a hardware implementation include the difficulty and expense of making further improvements or of fixing bugs, the increased development time, months rather than days, and the decreased flexibility. For instance, a hardware RAID controller may not provide any means for the kernel to influence the order or location of individual block reads and writes, even if the kernel has special information about the workload that would enable it to improve the input-output performance. Secondary storage structure. Mass storage structure. The file system can be viewed logically as consisting of three parts. In previous chapters, we examined the user and programmer interface to the file system. In previous chapters, we described the internal data structures and algorithms used by the operating system to implement this interface. In this chapter, we begin a discussion of file systems at the lowest level, the structure of secondary storage. We first described the physical structure of magnetic disks and magnetic tapes. We then described disk scheduling algorithms which schedule the order of disk input-outputs to maximize performance. Next, we discuss disk formatting and management of boot blocks, damaged blocks, and swap space. We conclude with an examination of the structure of RAID systems. Overview of mass storage structure. In this section, we present a general overview of the physical structure of secondary and tertiary storage devices. Magnetic disks. Magnetic disks provide the bulk of secondary storage for modern computer systems. Conceptually, disks are relatively simple. Figure below shows moving head disk mechanism. Each disk platter has a flat circular shape like a CD. Common platter diameters range from 1.8 to 3.5 inches. The two surfaces of a platter are covered with a magnetic material. We store information by recording it magnetically on the platters. A read-write head flies just above each surface of every platter. The heads are attached to a disk arm that moves all the heads as a unit. The surface of a platter is logically divided into circular tracks which are subdivided into sectors. The set of tracks that are at one arm position makes up a cylinder. There may be thousands of concentric cylinders in a disk drive, and each track may contain hundreds of sectors. The storage capacity of common disk drives is measured in gigabytes. When the disk is in use, a drive motor spins it at high speed. Most drives rotate 60 to 250 times per second, specified in terms of rotations per minute (RPM). Common drives spin at 5,400, 7,200, 10,000 and 15,000 RPM. Disk speed has two parts. The transfer rate is the rate at which data flow between the drive and the computer. The positioning time or random access time consists of two parts: the time necessary to move the disk arm to the desired cylinder, called the seek time, and the time necessary for the desired sector to rotate to the disk head, called the rotational latency. Typical disks can transfer several megabytes of data per second, and they have seek times and rotational latencies of several milliseconds. Because the disk head flies on an extremely thin cushion of air measured in microns, there is a danger that the head will make contact with the disk surface. Although the disk platters are coated with a thin protective layer, the head will sometimes damage the magnetic surface. This accident is called a head crash. A head crash normally cannot be repaired. The entire disk must be replaced. A disk can be removable, allowing different disks to be mounted as needed. Removable magnetic disks generally consist of one platter held in a plastic case to prevent damage while not in the disk drive. Other forms of removable disks include CDs, DVDs and Blu-ray disks, as well as removable flash memory devices known as flash drives, which are a type of solid-state drive. A disk drive is attached to a computer by a set of wires called an input-output bus. Several kinds of buses are available, including Advanced Technology Attachment (ATA), Serial Attachment (SATA), eSATA, Universal Serial Bus (USB), and Fiber Channel (FC). The data transfers on a bus are carried out by special electronic processes called controllers. The host controller is the controller at the computer end of the bus. A disk controller is built into each disk drive. To perform a disk input-output operation, the computer places a command into the host controller, typically using memory-mapped input-output ports. The host controller then sends the command via messages to the disk controller, and the disk controller operates the disk drive hardware to carry out the command. Disk controllers usually have a built-in cache. Data transfer at the disk drive happens between the cache and the disk surface, and data transfer to the host at fast electronic speeds occurs between the cache and the host controller. Solid-state disks. Sometimes old technologies are used in new ways as economics change or the technologies evolve. An example is the growing importance of solid-state disks or SSDs. Simply described, an SSD is non-volatile memory that is used like a hard drive. There are many variations of this technology, from DRAM with a battery to allow it to maintain its state in a power failure through flash memory technologies like single-level cell SLC and multi-level cell MLC chips. SSDs have the same characteristics as traditional hard disks but can be more reliable because they have no moving parts and faster because they have no seek time or latency. In addition, they consume less power. However, they are more expensive per megabyte than traditional hard disks, have less capacity than the larger hard disks, and may have shorter lifespans than hard disks, so their uses are somewhat limited. One use for SSDs is in storage arrays, where they hold file system metadata that require high performance. SSDs are also used in some laptop computers to make them smaller, faster, and more energy efficient. Because SSDs can be much faster than magnetic disk drives, standard bus interfaces can cause a major limit on throughput. Some SSDs are designed to connect directly to the system bus, PCI for example. SSDs are changing other traditional aspects of computer design as well. Some systems use them as a direct replacement for disk drives, while others use them as a new cache tier, moving data between magnetic disks, SSDs, and memory to optimize performance. In the remainder of this chapter, some sections pertain to SSDs while others do not. For example, because SSDs have no disk head, disk scheduling algorithms largely do not apply. Throughput and formatting, however, do apply. Magnetic tapes. Magnetic tape was used as an early secondary storage medium. Although it is relatively permanent and can hold large quantities of data, its access time is slow compared with that of main memory and magnetic disk. In addition, random access to magnetic tape is about 1,000 times slower than random access to magnetic disks, so tapes are not very useful for secondary storage. Tapes are used mainly for backup, for storage of infrequently used information, and as a medium for transferring information from one system to another. A tape is kept in a spool and is wound or rewound past a read-write head. Moving to the correct spot on a tape can take minutes, but once positioned, tape drives can write data at speeds comparable to disk drives. Tape capacities vary greatly depending on the particular kind of tape drive, with current capacities exceeding several terabytes. Some tapes have built-in compression that can more than double the effective storage. Tapes and their drivers are usually categorized by width, including 4, 8, and 19 millimeters and 1/4 and 1/2 inch. Some are named according to technology such as LTO5 and SDLT. Stable storage implementation. We introduced the read-ahead log, which requires the availability of stable storage. By definition, information residing in stable storage is never lost. To implement such storage, we need to replicate the required information on multiple storage devices, usually disks, with independent failure modes. We also need to coordinate the writing of updates in a way that guarantees that a failure during an update will not leave all the copies in a damaged state, and that, when we are recovering from a failure, we can force all copies to a consistent and correct value even if another failure occurs during the recovery. In this section, we discuss how to meet these needs. A disk write results in one of three outcomes: successful completion, the data were written correctly on disk; partial failure, a failure occurred in the midst of transfer, so only some of the sectors were written with the new data, and the sector being written during the failure may have been corrupted; total failure, the failure occurred before the disk write started, so the previous data values on the disk remain intact. Whenever a failure occurs during writing of a block, the system needs to detect it and invoke a recovery procedure to restore the block to a consistent state. To do that, the system must maintain two physical blocks for each logical block. An output operation is executed as follows: write the information onto the first physical block. When the first write completes successfully, write the same information onto the second physical block. Declare the operation complete only after the second write completes successfully. During recovery from a failure, each pair of physical blocks is examined. If both are the same and no detectable errors exist, then no further action is necessary. If one block contains a detectable error, then we replace its contents with the value of the other block. If neither block contains a detectable error, but the blocks differ in content, then we replace the content of the first block with that of the second. This recovery procedure ensures that a write to stable storage either succeeds completely or results in no change. We can extend this procedure easily to allow the use of an arbitrarily large number of copies of each block of stable storage. Although having a large number of copies further reduces the probability of a failure, it is usually reasonable to simulate stable storage with only 2 copies. The data in stable storage are guaranteed to be safe unless a failure destroys all the copies. Because waiting for a disk writes to complete synchronous input-output is time-consuming, many storage arrays add NVRAM as a cache. Since the memory is non-volatile, it usually has battery power to back up the unit's power. It can be trusted to store the data en route to the disks. It is thus considered part of the stable storage. Writes to it are much faster than to disk, so performance is greatly improved. Swap space management. Swapping was discussed in some previous section where we discussed moving entire processes between disk and main memory. Swapping in that setting occurs when the amount of physical memory reaches a critically low point and processes are moved from memory to swap space to free available memory. In practice, very few modern operating systems implement swapping in this fashion. Rather, systems now combine swapping with virtual memory techniques and swap pages, not necessarily entire processes. In fact, some systems now use the terms swapping and paging interchangeably, reflecting the merging of these two concepts. Swap space management is another low-level task of the operating system. Virtual memory uses disk space as an extension of main memory. Since disk access is much slower than memory access, using swap space significantly decreases system performance. The main goal for the design and implementation of swap space is to provide the best throughput for the virtual memory system. In this section, we discuss how swap space is used, where swap space is located on disk, and how swap space is managed. Swap space use. Swap space is used in various ways by different operating systems depending on the memory management algorithms in use. For instance, systems that implement swapping may use swap space to hold an entire process image, including the code and data segments. Paging systems may simply store pages that have been pushed out of main memory. The amount of swap space needed on a system can therefore vary from a few megabytes of disk space to gigabytes depending on the amount of physical memory, the amount of virtual memory it is backing, and the way in which the virtual memory is used. Note that it may be safer to overestimate than to underestimate the amount of swap space required, because if a system runs out of swap space, it may be forced to abort processes or may crash entirely. Overestimation wastes disk space that could otherwise be used for files, but it does no other harm. Some systems recommend the amount to be set aside for swap space. Solaris, for example, suggests setting swap space equal to the amount by which virtual memory exceeds pageable physical memory. In the past, Linux has suggested setting swap space to double the amount of physical memory. Today, that limitation is gone, and most Linux systems use considerably less swap space. Some operating systems, including Linux, allow the use of multiple swap spaces, including both files and dedicated swap partitions. These swap spaces are usually placed on separate disks so that the load placed on the input-output system by paging and swapping can be spread over the system's input-output bandwidth. Swap space location. A swap space can reside in one of two places. It can be carved out of the normal file system, or it can be in a separate disk partition. If the swap space is simply a large file within the file system, normal file system routines can be used to create it, name it, and allocate its space. This approach, though easy to implement, is inefficient. Navigating the directory structure and the disk allocation data structures takes time and possibly extra disk accesses. External fragmentation can greatly increase swapping times by forcing multiple seeks during reading or writing of a process image. We can improve performance by caching the block location information in physical memory and by using special tools to allocate physically contiguous blocks for the swap file, but the cost of traversing the file system data structures remains. Alternatively, swap space can be created in a separate raw partition. No file system or directory structure is placed in this space. Rather, a separate swap space storage manager is used to allocate and deallocate the blocks from the raw partition. This manager uses algorithms optimized for speed rather than for storage efficiency, because swap space is accessed much more frequently than file systems when it is used. Internal fragmentation may increase, but this trade-off is acceptable because the life of data in the swap space generally is much more shorter than that of files in the file system. Since swap space is reinitialized at boot time, any fragmentation is short-lived. The raw partition approach creates a fixed amount of swap space during disk partitioning. Adding more swap space requires either repartitioning the disk, which involves moving the other file system partitions, or destroying them and restoring them from backup, or adding another swap space elsewhere. Some operating systems are flexible and can swap both in raw partitions and in file system space. Linux is an example. The policy and implementation are separate, allowing the machine's administrator to decide which type of swapping to use. The trade-off is between the convenience of allocation and management in the file system and the performance of swapping in raw partitions. Swap space management. An example. We can illustrate how swap space is used by following the evolution of swapping and paging in various Unix systems. The traditional Unix kernel started with an implementation of swapping that copied entire processes between contiguous disk regions and memory. Unix later evolved to a combination of swapping and paging as paging hardware became available. In Solaris 1 Sun OS, the designers changed standard Unix methods to improve efficiency and reflect technological developments. When a process executes, text segment pages containing code are brought in from the file system, accessed in main memory, and thrown away if selected for pageout. It is more efficient to reread a page from the file system than to write it to swap space and then reread it from there. Swap space is only used as a backing store for pages of anonymous memory, which includes memory allocated for the stack, heap, and uninitialized data of a process. More changes were made in later versions of Solaris. The biggest change is that Solaris now allocates swap space only when a page is forced out of physical memory, rather than when the virtual memory page is first created. This scheme gives better performance on modern computers, which have more physical memory than older systems and tend to page less. Linux is similar to Solaris in that swap space is used only for anonymous memory, that is, memory not backed by any file. Linux allows one or more swap areas to be established. A swap area may be in either a swap file on a regular file system or a dedicated swap partition. Each swap area consists of a series of 4 KB page slots which are used to hold swapped pages. Associated with each swap area is a swap map, an array of integer counters, each corresponding to a page slot in the swap area. If the value of a counter is 0, the corresponding page slot is available. Values greater than 0 indicate that the page slot is occupied by a swapped page. The value of the counter indicates the number of mappings to the swapped page. For example, a value of 3 indicates that the swapped page is mapped to 3 different processes, which can occur if the swapped page is storing a region of memory shared by 3 processes. The data structures for swapping on Linux systems are shown in figure. Synchronous and asynchronous input-output. There are 2 types of input-output synchronization: synchronous input-output and asynchronous input-output. Asynchronous input-output is also referred to as overlapped input-output. In synchronous file input-output, a thread starts an input-output operation and immediately enters a wait state until the input-output request has completed. A thread performing asynchronous file input-output sends an input-output request to the kernel by calling an appropriate function. If the request is accepted by the kernel, the calling thread continues processing another job until the kernel signals to the thread that the input-output operation is complete. It then interrupts its current job and processes the data from the input-output operation as necessary. The 2 synchronization types are illustrated in the following figure. In situations where an input-output request is expected to take a large amount of time, such as a refresh or backup of a large database or a slow communications link, asynchronous input-output is generally a good way to optimize processing efficiency. However, for relatively fast input-output operations, the overhead of processing kernel input-output requests and kernel signals may make asynchronous input-output less beneficial, particularly if many fast input-output operations need to be made. In this case, synchronous input-output would be better. The mechanisms and implementation details of how to accomplish these tasks vary depending on the type of device handle that is used and the particular needs of the application. In other words, There are usually multiple ways to solve the problem. Synchronous and asynchronous input-output considerations. If a file or device is opened for synchronous input-output, that is, file_flag_overlapped is not specified, subsequent calls to functions such as writeFile can block execution of the calling thread until one of the following events occurs. The input-output operation completes, in this example, a data write. An input-output error occurs, for example, the pipe is closed from the other end. An error was made in the call itself, for example, one or more parameters are not valid. Another thread in the process calls the cancel synchronous IO function using the blocked thread's thread handle, which terminates input-output for that thread, failing the input-output operation. The blocked thread is terminated by the system, for example, the process itself is terminated, or another thread calls the terminate thread function using the blocked thread's handle. This is generally considered a last resort and not good application design. In some cases, this delay may be unacceptable to the application's design and purpose, so application designers should consider using asynchronous input-output with appropriate thread synchronization objects such as input-output completion ports. A process opens a file for asynchronous input-output in its call to create file by specifying the file_flag_overlapped flag in the wFlag and attributes parameter. If file_flag_overlapped is not specified, the file is opened for synchronous input-output. When the file has been opened for asynchronous input-output, a pointer to an overlapped structure is passed into the call to read file and write file. When performing synchronous input-output, this structure is not required in calls to read file and write file. Although create file is the most common function to use for opening files, disk volumes, anonymous pipes, and other similar devices, input-output operations can also be performed using a handle typecast from other system objects such as a socket created by the socket or a sep functions. Handles to directory objects are obtained by calling the create file function with the file_flag_backup_semantics attribute. Directory handles are almost never used. Backup applications are one of the few applications that will typically use them. After opening the file object for asynchronous input-output, an overlap structure must be properly created, initialized, and passed into each call to functions such as read file and write file. Keep the following in mind when using the overlap structure in asynchronous read and write operations. Do not deallocate or modify the overlap structure or the data buffer until all asynchronous input-output operations to the file object have been completed. If you declare your pointer to the overlap structure as a local variable, do not exit the local function until all asynchronous input-output operations to the file object have been completed. If the local function is exited prematurely, the overlap structure will go out of scope and it will be inaccessible to any read file or write file functions it encounters outside of that function. You can also create an event and put the handle in the overlapped structure. The wait functions can then be used to wait for the input-output operation to complete by waiting on the event handle. As previously stated, when working with an asynchronous handle, applications should use care when making determinations about when to free resources associated with a specified input-output operation on that handle. If the handle is deallocated prematurely, read file or write file may incorrectly report that the input-output operation is complete. Further, the write file function will sometimes return true with a get last error value or error_success even though it is using an asynchronous handle which can also return false with error_IO_pending. Programmers accustomed to synchronous I/O design will usually release data buffer resources at this point because true and error_success signify the operation is complete. However, if input-output completion ports are being used with this asynchronous handle, a completion packet will also be sent even though the input-output operation completed immediately. In other words, if the application free resources after write file returns true with error_success in addition to in the input-output completion port routine, it will have a double free error condition. In this example, the recommendation would be to allow the completion port routine to be solely responsible for all freeing operations for such resources. The system does not maintain the file pointer on asynchronous handles to files and devices that support file pointers, that is, seeking devices, and therefore the file position must be passed to the read and write functions in the related offset data members of the overlapped structure. File pointer position for a synchronous handle is maintained by the system as data is read or written and can also be updated using the setFilePointer or setFilePointerX function. An application can also wait on the file handle to synchronize the completion of an input-output operation, but doing so requires extreme caution. Each time an input-output operation is started, the operating system sets the file handle to the non-signaled state. Each time an input-output operation is completed, the operating system sets the file handle to the signaled state. Therefore, if an application starts two input-output operations and waits on the file handle, there is no way to determine which operation is finished when the handle is set to the signaled state. If an application must perform multiple asynchronous input-output operations on a single file, it should wait on the event handle in the specific overlap structure for each input-output operation rather than on the common file handle. To cancel all pending asynchronous input-output operations, use either cancel IO. This function only cancels operations issued by the calling thread for the specified file handle. Cancel IOX. This function cancels all operations issued by the threads for the specified file handle. Use cancel synchronize IO to cancel pending synchronous input-output operations. The read file X and write file X functions enable an application to specify a routine to execute cFileIO completion routine when the asynchronous input-output request is completed. Tertiary storage structure. Would you buy a VCR that had inside it only one tape that you could not take out or replace? Or a DVD or CD player that had one disc sealed inside? Of course not. You expect to use a VCR or CD player with many relatively inexpensive tapes or discs. On a computer as well, using many inexpensive cartridges with one drive lowers the overall cost. Low cost is the defining character of tertiary storage, which we discuss in this section. Magnetic tape drives and their tapes and CD and DVD drives and platters are typically tertiary storage devices. The media, tapes and optical platters vary between worm, write once and read many times, and RW, read-write formats. Tertiary storage is not crucial to system performance, but it still must be managed. Some operating systems take on this task while others leave tertiary storage management to application programs. Some of the functions that operating systems can provide include mounting and unmounting media in devices, allocating and freeing the devices for exclusive use by processes, and migrating data from secondary to tertiary storage. Because cost is so important, in practice, tertiary storage is built with removable media. The most common examples are floppy disks, tapes, and read-only, write-once, and rewritable CDs and DVDs. Many other kinds of tertiary storage devices are available as well, including removable devices that store data in flash memory and interact with the computer system via a USB interface. Removable disks. Removable disks are one kind of tertiary storage. Floppy disks are an example of removable magnetic disks. They are made from a thin, flexible disk coated with magnetic material and enclosed in a protective plastic case. Although common floppy disks can hold only about 1 MB, similar technology is used for removable magnetic disks that hold more than 1 GB. Removable magnetic disks can be nearly as fast as hard disks, although the recording surface is at greater risk of damage from scratches. A magneto-optic disc is another kind of removable disc. It records data on a rigid platter coated with magnetic material, but the recording technology is quite different from that for a magnetic disc. The magneto-optic head flies much farther from the disc surface than a magnetic disc head does, and the magnetic material is covered with a thick protective layer of plastic or glass. This arrangement makes the disc much more resistant to head crashes. The drive has a coil that produces a magnetic field. At room temperature, the field is too large and too weak to magnetize a bit on the disc. To write a bit, the disc head flashes a laser beam at the disc surface. The laser is aimed at a tiny spot where a bit is to be written. The laser heats the spot, which makes the spot susceptible to the magnetic field. Now the large, weak magnetic field can record a tiny bit. The magneto-optic head is too far from the disk surface to read the data by detecting the tiny magnetic fields in the way that the head of a hard disk does. Instead, the drive reads a bit using a property of laser light called the Kerr effect. When a laser beam is bounced off a magnetic spot, the polarization of the laser beam is rotated clockwise or counterclockwise depending on the orientation of the magnetic field. This rotation is what the head detects to read a bit. Another category of removable disk is the optical disk. Optical disks do not use magnetism at all. Instead, they use special materials that can be altered by laser light to have relatively dark or bright spots. One example of optical disc technology is the phase change disc, which is coated with a material that can freeze into either a crystalline or an amorphous state. The crystalline state is more transparent and hence a laser beam is brighter when it passes through the material and bounces off the reflective layer. The phase change drive uses laser light at 3 different powers: low power to read data, medium power to erase the disk by melting and refreezing the recording medium into the crystalline state, and high power to melt the medium into the amorphous state to write to the disk. The most common examples of this technology are the re-recordable CD read-write and DVD read-write. The kinds of disks just described can be used over and over. They are called read-write disks. In contrast, write once, read many times worm disks can be written only once. An old way to make a worm disk is to manufacture a thin aluminum file sandwiched between 2 glasses or plastic platters. To write a bit, the drive uses a laser light to burn a small hole through the aluminum. This burning cannot be reversed. Although it is possible to destroy the information on a worm disk by burning holes everywhere, it is virtually impossible to alter data on the disk because holes can only be added, and the ECC code associated with each sector is likely to detect such additions. Worm disks are considered durable and reliable because the metal layer is safely encapsulated between the protective glass or plastic platters, and magnetic fields cannot damage the recording. A newer write-once technology records on an organic polymer die instead of an aluminum layer. The die absorbs laser light to form marks. This technology is used in the recordable CD-write and DVD-write. Read-only discs such as CD-ROM and DVD-ROM come from the factory with the data pre-recorded. They use technology similar to that of worm discs, although the bits are pressed, not burnt, and they are very durable. Most removable discs are slower than their non-removable counterparts. The writing process is slower, as are rotation and sometimes seek time. Transforming input-output requests to hardware operations. Earlier, we described the handshaking between a device driver and a device controller, but we did not explain how the operating system connects an application request to a set of network wires or to a specific disk sector. Consider, for example, reading a file from disk. The application refers to the data by a file name. Within a disk, the file system maps from the file name through the file system's directories to obtain the space allocation of the file. For instance, in MS-DOS, the name maps to a number that indicates an entry in the file access table, and that table entry tells which disk blocks are allocated to the file. In Unix, the name maps to an inode number, and the corresponding inode contains the space allocation information. But how is the connection made from the file name to the disk controller, the hardware port address, or the memory-mapped controller registers? One method is that used by MS-DOS, a relatively simple operating system. The first part of an MS-DOS file name, preceding the colon, is a string that identifies a specific hardware device. For example, C: is the first part of every file name on the primary hard disk. The fact that C: represents the primary hard disk is built into the operating system. C: is mapped to a specific port address through a device table. Because of the colon separator, the device namespace is separate from the file system namespace. This separation makes it easy for the operating system to associate extra functionality with each device. For instance, it is easy to invoke spooling on any files written to the printer. If, instead, the device namespace is incorporated in the regular file system namespace, as it is in Unix, the normal file system name services are provided automatically. If the file system provides ownership and access control to all file names, then devices have owners and access control. Since files are stored on devices, such an interface provides access to the input-output system at two levels. Names can be used to access the device themselves or to access the files stored on the devices. Unix represents device names in the regular file system namespace. Unlike an MS-DOS file name, which has a colon separator, a Unix path name has no clear separation of the device portion. In fact, no part of the path name is the name of a device. Unix has a mount table that associates prefixes of path names with specific device names. To resolve a path name, Unix looks up the name in the mount table to find the longest matching prefix. The corresponding entry in the mount table gives the device name. This device name also has the form of a name in the file system namespace. When Unix looks up this name in the file system directory structures, it finds not an inode number but a major-minor device number. The major device number identifies a device driver that should be called to handle input-output to this device. The minor device number is passed to the device driver to index into a device table. The corresponding device table entry gives the port address or the memory-mapped address of the device controller. Modern operating systems gain significant flexibility from the multiple stages of lookup tables in the path between a request and a physical device controller. The mechanisms that pass requests between applications and drivers are general. Thus, we can introduce new devices and drivers into a computer without recompiling the kernel. In fact, some operating systems have the ability to load device drivers on demand. At boot time, the system first probes the hardware buses to determine what devices are present. It then loads in the necessary drivers either immediately or when first required by an input-output request. We next describe the typical life cycle of an input-output request, blocking read request, as depicted in figure below. The figure suggests that an input-output operation requires a great many steps that together consume a tremendous number of CPU cycles. A process issues a blocking read function system call to a file descriptor of a file that has been opened previously. The system call code in the kernel checks the parameters for correctness. In the case of input, if the data are already available in the buffer cache, the data are returned to the process and the input-output request is completed. Otherwise, a physical input-output must be performed. The process is removed from the run queue and is placed on the wait queue for the device, and the input-output request is scheduled. Eventually, the input-output subsystem sends the request to the device driver. Depending on the operating system, the request is sent via a subroutine call or an in-kernel message. The device driver allocates kernel buffer space to receive the data and schedules the input-output. Eventually, the driver sends commands to the device controller by writing into the device control registers. The device controller operates the device hardware to perform the data transfer. The driver may poll for status and data, or it may have set up a DMA transfer into kernel memory. We assume that the transfer is managed by a DMA controller, which generates an interrupt when the transfer completes. The correct interrupt handler receives the interrupt via the interrupt vector table, stores any necessary data, signals the device driver, and returns from the interrupt. The device driver receives the signal, determines which input-output request has completed, determines the request's status, and signals the kernel input-output subsystem that the request has been completed. The kernel transfers data or return codes to the address space of the requesting process and moves the process from the wait queue back to the ready queue. Moving the process to the ready queue unblocks the process. When the scheduler assigns the process to the CPU, the process resumes execution at the completion of the system call. Conclusion. In this chapter, we have covered the following in detail: input-output systems, input-output hardware, application input-output interface, kernel input-output, subsystem, transforming input-output requests to hardware operations, performance, synchronous input-output and asynchronous input-output, file caching, secondary storage structure, disk scheduling, disk management, swap space management, disk reliability, stable storage implementation, tertiary storage structure, tertiary storage devices, operating system jobs, performance issues file system formats, CDFS, FAT, NTFS, XFAT, etc., kernel mode and user mode driver framework.